People are still trickling in. There's some late or early registration, but I think we should get started. We had a full program. Welcome to everybody, and I give the floor to Lello Stefanini, one of the founders and early sponsors of this conference, and he will give us some memories and the welcome to the conference. Please, Lello.
Good morning. Good morning, everybody. I apologize for being seated, but consider I'm standing up and strong. I'm really honored to be here to speak and to give a welcome on behalf of the organizing committee. I wasn't thinking at all about this story. A couple of days ago, Francesco Forti has phoned me and he said, Lello, are you going to give an opening speech, a welcome speech? He said, oh, me? What about? I know nothing about what's going on. I say, no, well, I think it's kind of a tradition, so you must continue to do it. So I'm here, I'm very happy, as I was saying you, but I certainly cannot give any illustration, any news about what's going on in this conference in the large field of advanced detector and story. So being, as Francesco won't say, one of here from a long time, I'll give you a very short, believe me, speech about what is being going on in this conference. The first time the conference was held in Tirrenia in 1980. 1980 is 43 years ago. The world was really different. Physics was different. Everything was different. Many young people here don't even were born. And a bit later, because we were lazy, much less organized than now, the proceedings were out. By then, the idea of the conference was one only item, a very, very fashionable topic, which is solid-state detectors. So the title of the conference was, as you see here, miniaturization of high-energy physics detectors. This was, by and large, a wrong prediction. Think of the bigness of things like CMS, I see Guido here, or CDF, or the experiment at SLAC or LAT. But consider the exceptional result obtained with the silicon vertex detector in every kind of storage thing, all of them. CERN, LHC, CERN, LEP, the Tevatron at Fermilab, the SLAC collider, and also I think which we are very, very careful about the application of those things. So medical imaging grew very much along this line. The attendance was small. There was about 130 participants, mostly the people interested in the field. You may find, it's hard to read there, but you may find still quite a few of them still here today. Anyway, how the thing evolved. In 83, in 86, the meeting was held at Riva del Sole, close to Castiglione della Pescaia, another beautiful place. But the conference room, I was talking with Angiolino yesterday evening, was far too small to accommodate all the people. And so in 89, which is an important date, we came here to the Biodola. 89 has for me, which I'm old enough to remember many things, a very topical year. A lot of things happened in that. To say one, Ceausescu, Romanian dictator, fell down. The Berlin Wall fell down. The Cold War ended, and the meeting went to Biodola. This is among those is a good news. Not only the location has changed, but also the general philosophy of the meeting. It was a sort of linear and natural evolution, not just one main topic, but a large spectrum of topics, mostly dedicated to high-energy physics, and so the collaboration with great laboratories like the Tevatron, CERN, and so on. So the frontier detector was the main aim. Slowly, but always going in the same direction, the second part of the logo, the frontier physics, has come on. And now, this year, but also in the year past, the range of topics we deal here is really very big. I show you this one. You look at this. New ideas for particle radiation, and then gravitational wave, technology transfer, front-end cryogenic quantum sensor, light detector. Thing I sometimes really no idea what's going on here. Also artificial intelligence and so on. But we have dealt with all sorts of things. And now the right question. But why? I feel very pleased to be here. But why me? I feel rather embarrassed. I remember once hearing an old professor everybody knows, Luigi Arialdo Radicati, saying, above a certain age, a sensible and good taste man shouldn't speak, shouldn't make public speech. And I agree with him completely. So I was really hesitate to come here. For several Italians that are here, as a proof of what I'm saying here, think of the useless and shameful speech given by a so-called big shot of the center-right politics in Italy. I don't want to make name, but everyone understands it. He should have done it. Arialdo had a reason. But, so, I'm certainly not anymore. As a friend was saying at CERN, giovane ambizioso, an ambition young juvenile. But this is part of my history, and I wanted to share with all of you. Many of you are particular friends of mine. The reason is I believe that the present and the future is based mostly on the past. And without the past history, it's really tough to go ahead. This is again a way of looking at story, which is topical of old men, not young men. Young men does everything well without any history and go ahead like this. But especially in this difficult, innovative, and imaginative field, the history is important. To have a way to relate what is new with what is old, and go ahead and go ahead and go ahead. I am through with this presentation. I promise I would have been very brief. And so I welcome you all here and really wish you a good stay and enjoy very much this fantastic place. Thank you.
Thank you very much, Lello, for this inspiring talk for the past and the future. Yeah, hopefully. Okay, so thank you again, and maybe
I move down.
Yeah, we can help you a little bit. Yeah, I have to say a few words first. Okay, I need to say a few words myself. Okay. And okay, a few words from the conference chair. I'm very pleased to organize this conference. We have an incredibly full attendance. We have about 400 registrants. We barely fit in this room. And I will just say a few words to start the meeting. So this is the structure of the meeting. You've seen it, but let me point out at some of the highlights. We have 3 awards sessions, actually. One is this morning for the Icfa Instrumentation Innovation in Detectors panel. Then we have the Menzione Award, which has become a tradition of this meeting, organized by the Frontier Detector for Frontier Meeting. And then during the gala dinner, we have the Young Scientist Award ceremony. We have 3 prizes this year. One funded by the Frontier Detector for Frontier Physics, one by Kaien, and one by Hamamatsu. So we are very glad that we can recognize the hard work of people, old and young, in this field. We have a very full session. Talk times are between 15 plus 5 and 17 plus 3, but the important point is the talk slot is 20. And we have to try to respect it, otherwise we'll get into the lunch break or dinner. On Tuesday, we have a special social event after dinner, a little concert here. And on Thursday, we have the gala dinner. Let me say a couple of words about posters. We have the poster session runs in the next room. It runs at the same time as the corresponding oral session. And we are trying to do a new format. Posters are shown on high-resolution monitors. We have 20 monitors running on the specific session, and there are between 1 and 3 posters on each monitor. Then we have 4 screens for the full session. You can navigate the full session, and there's 1 index screen at the entrance. The presenter of the posters should try to stand by their posters during the coffee breaks, just before and after the session, so to answer questions. There's a photo of the presenter on the poster, so you can actually recognize him or her and grab him or her during the coffee break to ask questions. There are buttons to navigate through the posters, and we have confidence that our experimental physicists will be able to figure out how to use them. And so this is the index screen, these are the session screen, this is the poster browser. There is also a overflow area in the next room. If this room is too full, or maybe you want to sit quiet, you can also follow streaming of the conference in the next room. A couple of comments on network. EduROM is available. We are having some technical issues, so for some people it doesn't work. We are working to solve the problem. I'm not sure we can succeed because it seems to be a little bit intricate. But the hotel wireless is pretty good, so you can of course use it. And also there is a 9FN web network can be accessed, but then you have to ask for a password at the conference desk. Please be considerate in the usage of the network. We have a good connection, but we are still in an island, so it's not like being in Fermilab or CERN, and so don't stream the conference on your computer, please, and use it with consideration. Some practicalities. Face masks are mandatory in the conference room, and so please use them. There are masks at the entrance. The speakers will remove the masks to be more understandable, but let's try to avoid any risks. You also should wear the conference badge at all times when you move around the grounds here. The lunches are at the Foco di Bosco, which is down this little road, and many of you have already seen it. The badge is your entrance ticket to the Foco di Bosco, so you should wear it. If you have a companion, you should go together so that the personnel recognize you. Also, there is a little annotation for people who booked independently of the conference. Then, if you want to have lunch at the conference, you need to pay for your lunch, and then you have to go to the Hermitage reception to pay for the lunch. We have many families, and so there's a mini club available during the session hours for children aged 4 or more, and so that you can attend the session freely. Also, during the break, you can use the beach here, whatever, even if you stay at other hotels, you can use the Hermitage beach. This is an important feature of the conference to have the beach in the lunch break. A couple of comments on the buses. Face masks are also mandatory on the buses. There are shuttle buses for people staying at hotels in the Procchio area, Golfo, Perla del Golfo, and Desiree. They leave at 8 from there and come here, and then they leave from here to the hotels at the end of the sessions in the evening. On Tuesday, they come back for the concert, and on Thursday, they come back for the gala dinner. So you will always have the possibility of coming here to participate in all activities. Final words on proceedings. No work is done until the paperwork is done. And so proceedings, please prepare proceedings that will be published in a special issue of Nuclear Instruments and Methods A, as been always the case for this conference. The paper length is limited, 4 pages for talks and 2 pages for posters. There are instructions on the Indico side. Submission deadline is June 30. And let's try to stay with that. And that's all for the introduction. Enjoy the conference. And I now give the floor to our distinguished speaker, Jan Shipsey from Oxford University, who will present the Icfa roadmap for R&D in a very comprehensive way. So let's see if we can open that. All right. Okay, this should work. Yes, this works. I don't know how to. You do need that? Okay. Yeah, no, it doesn't work because this is mirrored the screen.
Let's just go to, how do I go back?
I'm sorry. You prefer?
Yeah, I can use this. Okay. Okay, so thank you so much for the very kind invitation. It's absolutely brilliant to be here. I've been asked to talk about the great questions in our field and the technologies that will achieve the ambitions that we will hold. And I'll do that from the perspective of the Icfa detector roadmap. So APEC, NUPEC, and Icfa, members of all 3 communities are here today, are united in seeking to understand the fundamental constituents of our universe and the forces between them, and to apply that knowledge to understand the birth, the evolution, and the ultimate fate of the universe, how the primordial soup here turns into the remarkable universe that we inhabit. And from the discovery of the electron in 1896, to the nucleus in 1911, to the Higgs boson in 2012, our communities have revolutionized the human understanding of our cosmos, its underlying code, its structure, and its evolution. And it's culminated in 2 remarkable prevailing theories, the particle physics standard model and the cosmology standard model. And both of these have been achieved primarily through instrumentation, through observing, through looking, through touching the universe. And the tools that we use to do this are very broad. Accelerators are our primary tool, but we use non-accelerator techniques, astrophysical and cosmological observations as well. And they all have a critical role and a complementary role to play. Our community has detected and measured energies over 24 orders of magnitude, from the cosmic microwave background to the highest energy cosmic rays. And we've developed a rich spectrum of technologies to enable us to do so. But the potential now exists to revolutionize our knowledge of our cosmos again. Because everywhere we look, there are mysteries. We do not understand the Higgs field. We do not understand the nature of neutrinos. We don't understand the dark matter that binds our galaxy together or the dark energy that drives galaxies apart. We do not understand in a deep way what a quark really is, what a lepton is. We don't understand the origin of the matter-antimatter asymmetry of the universe. We don't understand the hierarchy problem, the mystery of why there are so many generations of quarks and leptons, how inflation at 10 to the minus 36 of a second caused a massive increase in the size of the universe in just 3 decades in time, and the mystery of gravity itself. Theory can tell you many explanations for these things, but we don't know which one is right. So we're very much in a data-driven era. It's the reason why we choose to be experimentalists. Physics is fundamentally an experimental science. So the gestation time to realize the tools and the experiments that we've used in the past, for example, the LHC and LIGO, was decades. And for the most ambitious future experiments, for example, the FCC system or the Einstein telescope, to take the data and seize the opportunities for discovery, we must develop the tools. That means the instrumentation and the facilities now. And if history is a guide, new directions in science are going to be launched by new tools much more often than they are by new concepts. The effect of a concept-driven revolution is to explain old things in new ways, but the effect of a tool-driven revolution is to discover things that have to be explained. And this is a truly profound reason, again, why we choose to be experimentalists. And these searches inspire us, and they inspire the generations that follow us. If you look at the faces of these young children in the control room at CERN, they're excited by science. So we must do what Galileo told us, measure what is measurable and make measurable what is not so. Now, often in particle physics, when we've started out with a facility and a goal in mind, what we've ended up discovering is not what we expected at all. And so here's a bunch of facilities. The green is the original purposes, and this is what was actually discovered. Evidence for the Z and the W, the fact that there were 2 kinds of neutrino, CP violation, the charm quark, the bottom quark, the top quark, the tau lepton, the increasing PP cross-section that indicated that the Higgs or something else must tame those cross-sections. Neutrino oscillations, the gluon, and dark energy. None of the anticipated discoveries were how it turned out. It was much richer than that. Nature is far more interesting than we can imagine simply by theorizing. And so, however, many of these discoveries would have not been possible without precision instruments. They're the key to discovery when we're exploring new territory, and we explore new territory all the time. It's everywhere we look, including at the LHC. And the technologies that we develop are broadly applicable across our 3 fields and are synergistically developed. So for the technology classification to build the Icfa detector roadmap, we divided the technologies into 8 types. And each of these is incredibly broad and does a huge amount of science. And just look at one example, the photosensor. So the photosensor can tell us about particle ID. It can tell us about the cosmos. It can measure high-energy cosmic rays and high-energy neutrinos. And it plays a key part in the CMS and ATLAS and LHC experiments, and also searches for dark matter. It's incredibly broad. And the reason it's so broad is because photons are everywhere. And if you look at the APEC flagship research infrastructures, 5 of them depend critically on photosensors. This is CTA, high energy gamma ray. The future is photo detectors, silicon photomultipliers for photon and particle detection. Now, ways to improve these through digital silicon photomultipliers and more intelligence, but they're also common requirements with dark matter and DUNE for the future as well. Detecting high-energy neutrinos in ice. IceCube, Generation 2, want to increase the annual rate of observed cosmic neutrinos by a factor of 10 and detect sources 5 times fainter than their predecessors. And they'll do this through advanced multi-anode phototubes. Some are being shown as descending into the ice from a previous installation. And here are the upgrades now. One of these was developed by KM3Net, demonstrating the synergy, and this is what the future will look like. For today, we search with xenon and LZ in mass ranges up to about 10 tons. But the future is Darwin, a liquid xenon TPC, 200 tons, The choice of radio-pure photosensor technology to avoid giving false positives is crucial. The baseline is PMTs, silicon photomultiplier tubes, and other options are under evaluation for the future. Agatar is the ultimate gamma-ray spectrometer. It consists of 362 kilograms of high-purity germanium. It's a high priority for the NUPEC long-range plan, and it's hoped to complete it by 2030. It reveals much about nuclear structure. The cosmic microwave background, the fingerprint of inflation. You measure this through transition edge sensors. Early days, you could put 330 on the sky. Today, 7,600, but we need to put 4,000 in LightBird, and we need to put 500,000 on the surface of the Earth. Very challenging, but lots of synergy, again, with dark matter detectors. And because the universe is expanding, everything is redshifted. The challenge in optical astronomy is that we don't have CCDs that can measure the red end of the spectrum. Particle physicist techniques for the SSC led to the creation of CCDs, which are now deployed in the Dark Energy Survey and will be deployed in the world's biggest digital camera, LSST CAM, first light in Chile in 2024. At the same time, the photosensors that we develop are important for applications in society. The BGO program at LEP played an important role in position emission tomography. And the development of large area hybrid pixel detectors for high energy physics experiments led to the realization that we could do the single photon counting that would enable a revolution in photon science and in medical imaging, materials analysis, spatial symmetry, and climate studies, and so on. The Icfa detector roadmap will lead to the development of new technologies like these that hold the promise to be as broadly applicable and equally transformative. Now, this is Atlas. It could have been CMS, two remarkable cathedrals. And in many experiments, many classes of detector come together, working in synchronous harmony to reveal the mysteries of nature. And so we have to capture that as well in the Icfa roadmap across the classes of technology. It's also true for the electron-ion collider coming online, at least beams from 2030, so concurrent with the high luminosity LHC, will be a revolution in QCD. This is actually one of the detectors, and if you look at what's inside actually, it's the same type of detection mechanisms that we use in the LHC experiments and previously in STAR at RIC. And nuclear physics and particle physics communities are working side by side to realize this. If you go to FAIR and see Panda being built, you see it's a fixed target experiment that's designed to study aspects of the weak and the strong interaction. But the technologies inside it are the same ones that we use in particle physics, and the same is true for the CPM experiment at FAIR as well. If you look at the future of gravitational waves, the connections there are somewhat different. As you know, LIGO and Virgo are CERN-recognized experiments as MOUs between CERN, ENFN, and NICEF for the Einstein telescope. And there's synergies and work ongoing now on R&D for vacuum instrumentation, for underground construction, for vacuum beam tube construction, bake-out and cryogenics and controls. And it's very, very clear that the community that we've developed, e.g. CERN, has developed incredible experience in governance and implementation of big science projects, and ET should build upon this. So the current flagship for us is the NHC. It's been already a remarkable discovery machine, but much more is to come. Only 4% of the collisions that we plan to collect have so far been collected. Run 3 and the high luminosity NHC, I guarantee you, will be immensely exciting and transformative. And we must recognize this and tell our funders how transformative it will be, because doing so will help to pave the way for further funding for future ambitious accelerators. So that future is the FCC coming online in the E+E- format in 2040 or so, with a Hadron machine to follow. Now, at the LHC and at future Hadron Colliders, events are busy, require hardware and software triggers and high radiation levels, whereas at E+E- machines, we have simple events, no need to trigger, full event reconstruction and modest radiation levels. And so very different approaches, but in both cases, R&D is essential. This is a proposal for FCC HH detector. It's huge, and radiation damage is the biggest challenge, whereas for the E+E- detectors, they're normal-sized, but unprecedented spatial resolution and low material budgets have to be achieved. We have to do detector R&D, and we have to do that now, because the technologies developed for the LHC took more than 20 years. And they grew out of technologies developed for earlier machines at earlier experiments. The technologies for the high luminosity LHC began in 2008, and we're installing and commissioning by 2029. So the technologies for the future, for 2050 and beyond, have to begin now in the development and the planning, and that's what the Icfa Detector Roadmap does. It tells us what that plan will be, not just for that, but also for non-accelerator experiments as well. So our fields have the following European strategies. They're community-driven, outlining our ambitions to address compelling open questions. Guidance is provided for funding authorities across Europe to develop resource-loaded research programs to enable our ambitions to be realized. And so the update to the European Strategy for Particle Physics in 2020 recognized the primacy of instrumentation and called on the community via Icfa to define a global detector R&D roadmap. And that's the roadmap, and that's the link. We looked at the future physics program, identifying the main technology R&D to be met so that the detectors are not the limiting factor for the timeline. This is the detector context that we considered, accelerator and non-accelerator. We produced a 250-page report and an 8-page synopsis. The roadmap document structure, to navigate you through it, we had task forces for each technology and for training as well. The aim was to propose a time-ordered detector R&D program by detector research and development themes in terms of capabilities that are not currently achievable and driven by the facilities shown here. Now, there are many themes on this slide, and so you couldn't possibly read them. So let me just blow up one. This is the gas theme, and theme 1 is to improve the time and spatial resolution for gaseous detectors with long-term stability. Adding a little bit more detail, if you look here, the faded regions in these arrows indicate the typical time needed between the completion of the R&D and the readiness of the experiment at a given facility. The points are stepping stones. They show intermediate experiments from which we can learn. We can learn from ALICE to build future ILC-style detectors. We can learn from the high luminosity LHC how to build future FCC, HH detectors. And it should be emphasized that the future doesn't end when the arrows end, it's just not defined beyond that. And so gas detectors, looking at this first, they're ubiquitous. And so every chapter has a detector readiness matrix of each task force, and that focuses on the extent to which the R&D topic is mission critical to the program rather than the intensity of the research. And red means it must happen or the physics goals cannot be met. And so for gas detectors, this is the roles that they play from UN systems to tracking and particle ID. And these are the performance metrics that we wish to achieve. And these are the experiments as a function of time. And what you can see here is that it is very important for the radiation hardness and the reliability and longevity to address those questions for LHC experiments for LS4, for example. You can also look and see that for the far future, eco gases are incredibly important. They're also important here. And also fast timing is important, and large area integration for the pre-shower and calorimeters. And over here, you can see that right away now for PANDA and CBM, precision timing is important right now. And these detectors are very long in gestation. This is a picture of Sharpak, who invented the multi-well proportional chamber in the 1960s, won the Nobel Prize in 1992. This is Dave Nygren, invented the TPC in the 1970s, provides 3D space points. This is wider used TPC, ALICE, in 2010, and that evolution goes through the removal of the wire to construct microstructures that can create the large electric fields that give rise to gas amplification. These are micro-pattern gas detectors. That's a 50-year evolution. There are many ways to do this. Major players are Ode, who invented the technique, Sauli, and then Geometaris. And they have become widely used at the LHC for the upgrade because we can now make them with very low amounts of material, but also make them in large areas. And that's shown in the bottom left there. And so you see the micro-pattern gas detectors playing a very important role in ATLAS, CMS, ALICE, and COMPASS. But that time evolution was 50 years to develop the technology. We can look at liquid detectors. They're especially important for studying dark matter and for studying neutrinos. And on this slide, we've got all the detectors that we could think of, and in purple are the liquid detectors. They're liquid xenon, liquid argon, liquid helium, or water. And the modalities in which they work are charge, ionization, photons, or phonons. And many of these come together in the same detectors. But the detector started off with Rubia in 1977. He then built with his team Icarus, 670 tons, that operated at the Gran Sasso for many years, but is now at Fermilab as part of the short baseline neutrino program. And this is Dune's prototype at CERN, and the key research there are many types listed, but stability to very high voltages, demonstrating a very, very good uniformity of electric field in such a big device. And also in the future, increasing the charge light collection are key areas of research for Dune. Moving to solid state detectors, this is a map, courtesy of Alice. Many different silicon detector technologies have been used for particle tracking and for vertexing over the last 4 decades. And what's really remarkable is every decade the instrumented area has increased by a factor of 10, while the number of channels in the largest arrays have increased by a factor of 100. Solid-state detectors are now more radiation hard, and they're also used for calorimetry at time of flight. But we need improved precision, radiation hardness, and timing if we are to achieve our goals. And so this is the CMOS maps, monolithic sensors combining sensing and readout, ideal because of their low mass for the SCCEE, for example. And the real pathfinder here is the Alice ATS3 upgrade for Run 4, ultra-thin silicon that can be curved into cylinders. It's been demonstrated in beam tests that it can achieve 3-micron accuracy. Although the sensors can be small, you can stitch them, as demonstrated here. And by changing the processing technologies, we moved from Alpida to Malta and Modipix. However, to achieve the truly radiation-hard structures, we're going to have to use hybrid structures, sometimes 3D, and also high bandgap materials. This is a picture from the CMS experiment at the time of the Higgs discovery. There were 24 overlapping interactions in that one time that the beams crossed, and this was a Higgs to ZZ event. That was then. This is what it looks like in 2029 with 200 pileup. And the way to unpick that is with precise timing. High luminosity does mean large data sets, large pileup, and high radiation doses. And when you view the collision, it looks like a fog, but with timing, everything becomes clear. And the technologies of LGADs and silicon photomultipliers can address those challenges at the high luminosity LHC. And the experience is going to be crucial for future high-energy colliders. And LGADs, for example, are going to be incredibly useful well beyond HEP, for example, in medical physics, in synchrotron applications, in nuclear physics, and so on. In particle identification and photosensors, I already said quite a lot about that, but naturally radiation hardness is at the core of the R&D for the next generation of colliders. And silicon photomultipliers are the most active field. There's a lot of work still needs to be done on near UV and fast timing sensors, and with urgency as well. Quantum technologies are emerging and will be transformative for some fields of physics. Quantum technologies are of many different types, and there's no time to go through the details here, but there are many programs around the world being created. But this one plot shows you some of the potential. So we're plotting mass, and we're looking for dark matter. The blue lines are existing experiments that don't use overtly quantum technologies. So these are searches for WIMPs and searches for axions that are around a microelectron volt. But with the new technologies coming online, all of the light green areas there will be opened up for discovery. And so we could be discovering dark matter that way, or perhaps we discover it in a more traditional way. In calorimetry, the R&D has had a very, very long lead time. I mean, that's the duration of the stage for the experiment-specific final prototyping, the procurement, the production, the assembly, the commissioning, and the installation. And there are 3 themes here. The first is the enhanced electromagnetic energy and timing resolution most relevant to next decade for the ALICE and LHCb, for example, ALICE focal, so at left. And if you look at the results that are being achieved here, this is the culmination of 10 years of work. and much more work will be needed going forward. The second theme is particle flow based on high granularity calorimeters, and it's very, very important for the Higgs factories, and the options are dual readout or high granularity liquid argon or liquid xenon, or finely cemented crystals, or the very exciting particle flow based tracking calorimetry. And the third theme is extreme radiation hardness. In electronics, we need high-speed links and microelectronics that are much more advanced than ever before with small feature sizes. Because the feature size continues to decline, we can get more and more information on a wafer, but the cost of procuring is rising absolutely dramatically. We must work together across Europe and across the world to make these technologies affordable. And finally, integration. An example here is an ultra-low mass tracker. It all started out with STAR. Now mu3E is developing its own gas-cooled MAPS tracker. The R&D occurring for CLIC will lead to a solution for Alice for Run 4. And finally, training. So training is so important for all of us, younger and older. We've all got so much to learn. And it's especially important for the long timescale projects that we now face. So there's a specific recommendation in the program to create a systematic education program, including a standard master's in instrumentation for the whole of Europe. So the next step, Icfa was mandated by Council in December to work out how to implement the roadmap. Work is ongoing. The first implementation plan has been proposed. It's to establish new detector R&D collaborations at CERN, in addition to those that already exist, for all of the technologies that are not yet covered, because the R&D collaborations are incredibly successful at bringing us together to tackle difficult technical questions. Discussions with CERN Council and the funding agencies have started. There are three sets of general strategic recommendations as well. The first is that we must support R&D facilities. And this means making test beams more available, more irradiation facilities, larger doses delivered in shorter times, and large-scale prototyping facilities as well. The second is recognizing that we must support engineering for detector R&D. That's electrical engineering, ASIC design, but also mechanical design and advanced materials. Third, we must support our software, make it more available, and increase its performance. Fourth, the international coordination. That will happen through the R&D collaborations. The fifth one is to recognize that we have talent in the national labs and talent in the universities. We must find a distributed detector laboratory model that enables everybody to work together as one team. We need to establish long-term strategic funding programs because the ambition takes many years to realize. So we're calling for enhanced funding, and because we must repeat the World Wide Web, the magnetic resonance imaging and PET results and X-ray imaging of the past, and at the same time make new measurements that will reveal nature in a way that we've never seen before. We have to make sure that the candle can turn into the light bulb. And so finally, this is the last couple of slides. So many of the people in this room are very young, and behind you are many more people even younger than you, and we have to recognize that the vibrancy and creativity comes from young people. And so we've got to attract, nurture, recognize, and sustain the careers of R&D experts. That means recruiting them, paying them good salaries, providing permanent contracts, and the possibility to become professors at universities, even when their priority is instrumentation rather than the glory plot that you see on the BBC. And recognition through prizes and other awards. Industrial partnerships mean that we innovate and work with our colleagues in industry so that we're not lagging behind in, for example, microelectronics. And we must make sure that it's possible to publish in instrumentation journals for free, just as Scope 3 has made it possible to publish science results from CERN in the American Physical Society journals without paying a fee. So the roadmap was requested by the European strategy. It's a matrix structure displaying synergies between concurrent and subsequent projects. Discussions towards implementation are ongoing, and the roadmap should be updated in the future together with the European strategy by the community. And so we have wonderful facilities around the world to enable our science. Our field is global. We have to nurture those facilities and our people, and we have to build new facilities to enable us to understand our universe, which is, in a sense, our birthright. what makes us human is that we can ask these difficult questions. But at the same time, the science that we do has important value to society. And science, technology, engineering, and medicine are the best hope for our species to actually survive on this planet. And particle physics and its associated fields are a key part of that. At a very difficult time for the world, it's very, very easy to do what Michelangelo said we should not do. And that is, the greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and reaching our mark. That is simply not good enough. What we have to do is aim high, aim very high, or we will not realize the potential for our field or for our species. And our discoveries will be stalled, and we'll betray ourselves, everyone in this room, and the young people that follow us. Thank you very much.
Sorry, this is locked here. No. Let me use the other one, sorry. Thank you very much, Ian, for this wonderful introduction to the conference and inspiring talk. Maybe we can turn on the lights in the room again. And the floor is now open for questions. There's one over there, over here, maybe. Can you turn on the lights? Yeah, the question here. Yes.
I'm going to have to repeat the question because
thank you, Ian, for this brilliant talk. I would like to point out one thing. You make the point that we are building detectors that will operate in 20 years from now. And I would like to make the point, I'm sure I'm talking to the right audience here, that we are sitting on a very steep slope of improvement on our software capabilities. It will not be a Kalman filter that reconstructs our tracks in 20 years from now. It will be some artificial intelligence tool. So we risk a potential misalignment between what we build now and what will operate in 20 years in terms of reconstructing and extracting the information. And I think this has to be kept in mind, and we should get equipped with the tools that allow us to consider that factor in the overall design of our instruments, such that we don't overdo we inject redundancy in our instruments, but maybe redundancy is not what artificial intelligence requires, and we can spend our money better. So I encourage everybody to think about this elephant in the room, that we are going to build stuff that will be handled by artificial intelligence in 20 years from now. Thank you.
I would say that taking that into account, we have to more than ever, using that knowledge, develop and refine and improve technologies now, but with the plan that we should minimize the lead time to actually insert them, install them, such that we have as much as possible the most current state of the art. But in addition, we need to exploit intelligence. Intelligence both in the front end and intelligence in the back end. It's not impossible to imagine that in the future, our detectors will have enough intelligence that they'll realize that they're not quite cutting edge enough for the new physics they're beginning to sense. And in a way that our neurons rearrange themselves, their detectors will interconnect in different ways. We're obviously fixed today in very old-fashioned ideas which are cutting edge, but they're old-fashioned because we have cables everywhere. We use very slow data links. We do not put enough intelligence into the detector, front end or back end, but we know that every time we add more, and make the triggers cleverer and things like that, and employ more artificial intelligence, we see gains in every area that we look. And so we must continue to push on all of these in such a way, in such a flexible way, that the detectors that we build will not become old-fashioned at the time they turn on, but actually be adaptable to the new physics. This is a very ambitious thing to do, but we have the time to do that if we start now. This is a bit like a moonshot. It's going to be very, very difficult, but if the world works together, I believe it can be done. And it's also true to say that for some very interesting measurements, they don't require massive detectors. You actually have small tabletop, and there you can be versatile and change the detector every year. And so I think that both types of physics going forward will be important as we try to understand this incredible cosmos. Does that help answer the question? Which I think was an excellent question. Thank you.
More questions or comments? One over there.
Yeah. In the development of new technologies, in your opinion, is a sustainable process? Sustainability is an issue?
Is the sustainability of new technology an issue? Sustainability.
Sustainability. In what sense? In what sense sustainability? You mean is a field sustainable, or?
Yeah, for example, I mean gas detectors using different kind of gas development.
Ecological issues.
Yes, I mean, I think that the point is that we recognize that there are issues, and we're going out to look for solutions for that. Human beings are the most creative thing we have on this planet, and I believe that any challenge can be solved if we work hard enough. And so I'm not concerned about, I'm concerned that it's important. I'm concerned that we're trying to address it, but I do believe that we will. Mm-hmm. I mean, if you talk to your colleagues in the gas community, they're brilliant people. And they will find solutions. And they've demonstrated that over 50 years, from the work of Sharpak all the way through to the work of today, of people like Fabio Sauli and Yanis Triamataris.
Yeah, I think we should keep in mind sustainability.
Yes, absolutely. Absolutely, very important.
That's what should one.
That's right. That's right. I mean, for the politicians, it's very important that we make that clear. For our planet, it's very important that we make this clear. And for young people, they ask that question often.
Right.
Is your field actually sustainable? Are you actually damaging the environment with the massive amounts of power that might be needed to power some of these accelerators and so on? And so all these things have to be factored in. And CERN has a good program that's accentuating that now.
Okay, are there comments or questions? If not, let's thank our speaker again.
Thank you.
Nice introduction. And speaking about young people and enthusiasm of young people, maybe you may want to use this one. Armin Ilg from he's one representative of the early career researcher panel in the Icfa process, and yes, that's the. And so he's giving us the perspective of the early career researchers in terms of training, in terms of developing a career in instrumentation. And I hope this will be inspirational for younger people. There will be, I think, also space in the next room for more discussion. Try that if it works.
Can you hear me?
It should be turned on.
Hi. Can you hear me now?
Yes.
Yes? Okay, good. It should be in view full screen. If that's not. Yeah, that should be. Okay, do you have something? This one. Okay. Okay, thank you very much, and thank you for having me here. So I think the talk before this was a great start for the topic, so I can basically skip the first slide because you heard enough about all the mysteries that we have in particle physics and how long-term planning is needed for this. And obviously you heard before about the Icfa RNA detector on the roadmap. So this is that's really the goal of this Icfa program and of the update of the European particle physics strategy to plan for the future. And also there you heard that an E plus A minus Higgs factory is the highest priority for the European particle physics strategy as a next collider, with the long-term ambition of proton-proton collisions at the highest achievable energy. And actually, if you look at the timeline of the Future Circular Collider, for example, the last time I've seen was 2085. So that's even the generation after us young researchers here, or maybe 2 generations after. So this really shows us that we need to invest now in the experts that will conceptualize, design, build, and also operate these facilities well into the latter half of the century. And this is where another of these 20 strategies. So before you've seen some strategy statements from the particle physics strategy. And here there's another one, which is action point 7p, which is about early career researchers. And it states that the education and training for early career researchers is essential for them to thrive, and that supervision and training is needed. Also, one wants to increase the recognition of individuals developing and maintaining experiments, computing and software, and that equality, diversity, and inclusion should be at the heart of these activities. So this is really where the Icfa Early Career Researchers, or ECR panel, comes into place. So the scope of today is to explain you what the Icfa ECR panel is, what we do, and what we found out about issues that young researchers in instrumentation face in our field, and some ideas on what can be done to help them or us. So, a short disclaimer, this is obviously a huge topic. It quickly becomes very political, and I will only give an overview over this topic, and the idea is to get some discussion going during the week, that maybe there can be some initiatives afterwards. Okay, so the Icfa ECR panel is a follow-up of this of the input that ECRs gave to the 2020 strategy update, and you can find the link there, which summarizes these results. And that's actually a very good example. Like, I think in the whole strategy update process, ECRs were only specifically asked rather late in this process, and this is why so in the future we want to do it better, and this is why this panel was founded. And it should discuss, in a broad sense, everything about the future of the research field of particle physics, and it has an advisory role to Icfa. In total, we are 75 delegates, 3 from each Icfa country and major laboratories. There are 5 delegates that sit in the plenary Icfa and 1 that sits in the restricted Icfa. And we cover everything from PhD students all the way up to young assistant professors. And there are theoreticians, phenomenologists, and experimentalists all in there. So we try to cover a large diversity in the cultural background, in the career stage, and also in research. Down here you can find a list of working groups we have until now. So this whole process started last year, so it's still a bit, now we should have started up properly, and now we actually can do some work. So we have some career prospects working group, diversity in physics, electron-ion colliders, detector R&D networking, and instrumentation R&D. And the last point is what I want to focus here today. So the original idea was to collect some input, some ECR input on training in instrumentation. So there was some direct input from the Icfa ECR panel, which you can see on the right side here. So everything you see here was done by us. And there was a town hall meeting April last year, where we tried to understand what people are interested in, what we need, and to discuss what kind of questions we should circulate. And with this input, then we created a survey that was filled out by more than 470 ECRs from all over Europe, with mostly closed questions, but also many open questions where people could write down what their issues are, in which situation they are in, and so on. So these results were then presented in the Icfa Detector R&D Roadmap Symposium on Training, which is one of the Detector R&D task forces, I think. And they're also summarized in this report down here. So if you're interested in this, please have a look at this, and then you can get a cohesive overview of everything. So first, a few words about the profile of our participants. So this survey was distributed among ECR networks within experimental collaborations, and also other national or international lists. Of course, we are not social scientists, so these survey questions maybe are not perfect, but still they can give you a lot of qualitative data on issues that young people in instrumentation are facing, and especially the individual replies were very fruitful. Like people explaining, okay, I am part of this minority groups, and these are the issues I face in daily life. So we mostly had PhD students and postdocs answering, but also, for example, I think 30 or 40 engineers that were answering, and so it's quite diverse. Then we also asked whether people identify as an underrepresented minority in their field, which more than 25% answered with yes. And lastly, we also asked about the fraction of time spent working in instrumentation. And also there we can see a quite even share, which is very nice, because if you only ask the people that already are very late in their career and are working 100% in instrumentation, we will not understand why not more people are doing instrumentation. Okay, so overall, yes, there's very large variety in the survey response. And now let's go through the 3 main points that we found out. So first, about training and instrumentation, which was the original goal of this survey. So 30% had expressed an interest in instrumentation training in the past, but were not able to access it. And I think this is something that is really important to realize, that people are interested in instrumentation, but sometimes they just don't know where to start. And one reason for this is, you can see on the left side, so we asked the question how informed people think about opportunities in instrumentation training. And if you look at, so it goes from very uninformed on the left to very informed on the right, and you can see that only 15% of the people feel informed or very informed about opportunities. And most people are not happy about this. And this is something that has to be tackled. Because on the other side, if we ask people whether they would be willing to take on instrumentation if more training was available, then most people say yes. So give people the training and they will do the work for you. Okay, yeah. And also it's important that, so we also asked whether ECRs had some instrumentation training in their master or in their PhD. And we found out that these people were more likely to view instrumentation as a benefit to their career and as something that they enjoy. So again, training is crucial. Lastly, we also asked some questions about the kind of training that people took. So 61% stated that their experience of remote training or work in instrumentation was positive. So we all know that remote work and remote training is not easy, especially in instrumentation. But it's better than nothing, right? So that's something that we could emphasize more in the future. And lastly, 79% thought that their peer-to-peer training that they had was useful. So I think this is the way that we should train instrumentation, like peer-to-peer, because in this way you don't only learn things, but you also have a chance to network with people that also maybe are one career step ahead of you, and you can discuss also these issues with them. Okay, then we come to the second out of the 3 points, which is about instrumentation networks. So we all know that COVID-19 struck ECRs in instrumentation especially hard, exactly because hands-on training and work are crucial. So this is what you can see here on the left side. So we asked whether people are satisfied with their networking opportunities for ECRs in instrumentation. And half of the people are it's okay, but not many people are actually happy with it, which is really sad. And so 30% are not satisfied with networking opportunities. Of course, this was definitely influenced by the circulation time of the survey, which was April last year. But still, we also really realized that there are not many cross-experiment networks in instrumentation available. For example, there's not a single E-group that is targeting ECRs in instrumentation over different experiments. At least I didn't find one. And also, we want to ask a question how to support the increasing interdisciplinarity. So maybe we should more often have people working on silicon sensors and on gas sensors sitting together. So of course, so many people expressed that more workshops and more summer schools devoted fully to instrumentation are needed to connect those in different experiments. And equally important, even more important, is to properly advertise these events and create having some suited channels to connect the different communities. And this is really something that's lacking. Lastly, about diversity and inclusion. So I will again only cover a few key points because it's a very big topic. I think you can make a whole conference only about this. So there are still many gender identity related issues. For example, I think 10 respondents said that there were still often assumptions being made that women wouldn't want to get involved in instrumentation, and that they were being treated differently in meetings. So they were not taken seriously, or things were explained to them that they didn't ask for, and there's still quite some sexism in the workplace. On the other hand, something that probably you're also very aware of is geographical diversity. So if you are from a not so rich country, it's very difficult to get access to instrumentation training. And so overall we asked whether whether these people think that their identity as underrepresented minority has impacted their training experience. And actually, 42 out of these 126 people said that yes, there was an impact on their training experience. So this is something very important we need to keep in mind. So as I said before, remote training is not perfect, but this is an opportunity to lower the barriers in instrumentation. For example, due to travel, financial, or care-related issues. It's easier to be every morning in a week in a Zoom call on instrumentation than going to some far away, nice place, expensive place for 2 weeks. Okay, with this I come to my last slide with some ideas on action and some discussion points. So two of the key needs that we identified were that more networking opportunities are needed, especially for instrumentation. So the Icfa panel, we want to organize some panel discussion on instrumentation with both senior and young researchers in instrumentation. This is something that should be announced soon. Then there's a huge lack of information about instrumentation training. So last week I tried to collect information about instrumentation schools and particle physics, and I created this web page here that you can now also find on Google. I just found out today. So something like this, it's very easy. But if this is something that you think is useful, please send me your suggestions on things that I'm missing, because I'm definitely missing things, and I will add them here. And this could be a resource to have an overview over all these schools, because normally you need to go to 5-6 different web pages that you may or may not know, and then to find a school suitable to you. And I also didn't know about some of these schools because before I did the research. Overall, I want to emphasize that there's a lot of interest and enthusiasm in instrumentation within the ECR community. So here I mostly talked about issues, but that's what we want to improve, right? We need to discuss the issues in order to be able to solve them. And some possible discussion points during the week are listed here. I think there should be a flip chart in the other room there with the posters, and I will add some post-its and other like markers so you can write down your ideas or your issues and put them there. And maybe this could be a place for this discussion during the week. So inter-experimental networking opportunities is something that is very important. This could be discussed. Yeah, as I said, there's, as far as I know, not an instrumentation R&D e-group. This is something that could be created, like young instrumentation at CERN or young instrumentation in HEP, whatever, something like this. And yes, also on the other side here, there's some correlated efforts that I didn't have the time to talk about. So especially on career perspectives, there will also be a survey circulated within the next months or so, where we want to collect data specifically on career. Okay, that's it. So thank you very much, and enjoy this very networking opportunity, and maybe also the island a little bit. Thank you.
Thank you, Armin. Very nice presentation. Comments, questions? Over there, Silvia.
Thank you. It has really brilliant and inspiring. But the point that you touched the last has also to be really put on focus. I'm not longer in the group of young experimentalists, but in the contact with younger colleagues, there is clearly the perception that dedicating themselves so much to instrumentation, they will have much more difficult career perspectives. And this is a shame. And it is responsible of all of us. And it is very important that starting from bottom for you, younger colleagues, we overcome this difficulty, which is blocking the whole field at the end. In the previous brilliant talk by Jan, we have understood that without progress in detector, there will be no progress in physics. And the progress in detectors depends on giving you career perspectives. Okay, thank you.
Maybe
Yeah, thank you for your comments, Silvia.
maybe Charlotte can also share one slide could be interesting to you. Because as you say, so there can only be career opportunities if these things are recognized, and recognition is a big issue. So we also asked people whether they feel that their work is acknowledged within their working group and within their collaboration. And this is something that many people also expressed, that they don't feel that, like other people doing data analysis, they are saying that, okay, you're only doing some hardware, and hardware is seen as a burden. And that's again something that has to be changed from the bottom up. But we ourselves have to be proud of our own work and have to say, hey, our work is crucial and it's equivalent to data analysis.
Other comments? There, yeah, one over, maybe start over here. And no, it's not on.
You hear me?
Yes.
Yeah. There is another component in all this, and this is the industry that should accompany the building of new detectors. Okay, and actually, if one would do a geographical distribution of these companies, one would see that they are very concentrated in some places, and they are not overall. This is, for instance, in today's situation, making a lot of problems, okay? So I think that both in Jan's and your talk, I mean, this is a component that should be treated and analyzed.
Thank you. Yes,
Thank you. Yeah, actually, yeah, technology transfer and connection with companies is an important issue. I didn't say it in the beginning. We will have a roundtable with companies on Tuesday afternoon where we'll have an opportunity to hear development lines. And one of the things we have asked this company is to provide us some information about careers for people in companies, because I think instrumentation physicists do not have to look only at academia, but also industrial work is as exciting and as interesting and important. There was another question over there. Yes.
Yes, so thanks a lot, Ian, for this presentation, and also thanks for the organizers to have such a talk. I think this shows that we in this room are very much aware about that we have to bring up this situation of young researchers. The point I would like to make here is also related to what Silvia just said. I think it does not only have to be bottom up from the young people, but also from the elder one, because I mean, when we as instrumentalists submit a grant application for an early researcher group or for an ESE starting grant, I still think it's very difficult for us to convince the reviewer that we will have the chance to go towards a professorship, for example. So I think for you in this room, for the seniors, it's quite obvious that we have to establish more of these professorships. But for the majority of the professors, which are mainly in data analysis, I think you should also negotiate with your colleagues that such proposals should also be rated and admitted towards the direction of a professorship or towards permanent positions. I don't know what we are doing with this respect in the early researchers panel. Maybe you can comment a bit.
Yes, I mean, obviously we don't have so much negotiation power at the moment. I mean, I think we have to discuss this issue as broadly as we can, and that's what we should all try to do. Like in every time hardware work is being made small by other people, we have to stand up, I think. But yes, it needs to come from bottom up and from top down.
Okay, last question over there.
Thank you. Maybe building on this subject here, I wondered as an engineer in the field, actually, why so many schools of physics demand that to get a PhD, there must be data analysis. And I've seen this in many schools. Is this a specific problem that has been, for example, addressed or analyzed in the work of the panel? It's something I felt from the experience I had with the students. It's easier to get a PhD in instrumentation, maybe for someone coming from electronic engineer faculty, than sometimes from a physicist of many of the European universities. Is this a correct understanding, or?
I mean, from what I know is that if you're only doing analysis, it's easier to get to find a position to get a PhD with this than if you only do hardware. There are some positions nowadays where you only do instrumentation, but it's definitely not easy. But that's maybe
it's a complex question, but it's true. Many graduate schools require that to give you a PhD in physics that you have a full-blown data analysis, and that instrumentation work can only be a corner of your PhD year's work, which is often not true, in the sense that maybe you spend 2 years on instrumentation really, and then in the last 6 months you try to put together an analysis. I think this is a distortion of the system, and we should work with the academia to improve that. But I don't think there is any specific solution, but discussing this in the panel and maybe identifying that as an issue could be useful. Okay, thank you very much. I think that we should try to move on, and so let's thank our speaker again. And before the coffee break, we have our first award session of the conference, and let me call Professor Jan Shipsey again as chair this time of the Icfa IID panel. And you want to use this one? Yes. Yeah. Okay.
Okay, so what I would like to do is to introduce the inaugural Icfa Instrumentation Awards and then announce the winners. Able to hear me now? Yes. Yeah, okay. So for those that didn't hear what I said before, I'm going to introduce the awards, where they came from, why we're doing it, and then who the committee have selected for this year's inaugural awards. So for those of you that don't know, I certainly didn't know myself until a few years ago what actually Icfa is. Icfa is the International Committee for Future Accelerators, and it was actually created in 1976, and it's part of the International Union of Pure and Applied Physics, and so it's part of the leadership of our field. And if you look at the kind of people that are on Icfa, it's people like Fabiola Gianotti and Nigel Lockyer and his successor at Fermilab. So lab directors from around the globe, and people representing the different areas of the world, from Australasia to Asia to Europe and the Americas. And so there are 16 people on this committee. And the committee itself helps to identify and promote international collaboration that in its original conception was primarily only for very high energy accelerators. That's still a big part of it, but today it supports physics more broadly within our field to include some non-accelerator activities in its reports as well. So Icfa itself has 7 subpanels, and one of those subpanels is called the Icfa Instrumentation Innovation and Development Panel, and that panel was led for many, many years by the brilliant physicist Ariella Katai. And when she stepped down, the panel was reformed. I became the chair, and we have many wonderful members, including Francesco in the front row. So the goal of that panel is to stimulate across the whole world involvement in innovation and development of instrumentation, not just for future accelerators, but more broadly as well. And so there's 4 things that we do at the moment. 2 of those things are things we inherited from the previous panel. One of them are the edit schools. The first edit school was held, I think, in 2011 at CERN. It's a fantastic high-level instrumentation school for 50 students. It's held historically, it was once a year, and then it moved to once every 2 years, and then the pandemic came. And so it's restarting now. And the next schools in 2023 one will be in Asia at IHEP Beijing, and a second will be in the United States. And we will be making the announcement of which laboratory will host that in about 2 weeks. There's even the possibility of having 2 schools in the United States in 2023, because there's a huge demand for this school. It's an incredible learning opportunity. And anyone that's been to it will testify that it can launch your career in instrumentation. The second school that's also been run for many years is the Icfa Instrumentation School. So unlike EDIT, the Icfa School is distributed around the world, often in countries that are less developed. And the school that we had hoped to hold just before the pandemic started has been delayed, but will now happen in March of 2023 in Mumbai. So all of these schools are very advanced stages of planning. One of the things that we're very conscious of is that even though the schools are fantastic, at least everyone that goes to them says they are, we reach very few people in these schools compared to the potential. And as we just heard from the Early Career Researcher panel, there is a huge demand for these schools, and I think it would be great if we invited the chair of that panel to join our Icfa panel and make sure that we stay grounded and meet the needs of the younger people. So there's huge scope for more schools. Another thing that we do was we recognize that we do not celebrate instrumentation. We tend to celebrate our field, but we tend to stress the analyses and the physics results, none of which would be possible without the instrumentation. And so to recognize instrumentation more broadly, both nationally and internationally, we thought we should try to stimulate the creation of more prizes for instrumentation. Some of these can be done through national societies in Italy or in Germany or in the UK or the US. And in fact, we had some success in creating a new instrumentation prize in the US about 5 years ago. However, there was no world prize. And given the incredible people that have done incredible instrumentation over the years and have not been recognized globally for that as much as they could be, as well as the young people coming through, we thought it was very good to create a prize. And so we worked together on a proposal, and we presented it, as we got sub-panels, we presented it to Icfa, which is the main panel, and they agreed to it in July of 2021. And there are two prizes, one for a senior scientist and one for an early career scientist. And we hoped at the time that the first awards would be possible by, roughly speaking, now. And you'll see in a moment that that was in fact possible. We kept to our timeline. The fourth thing that we do, and we're very excited about this too, is we want to create a new type of instrumentation studentship that would enable people from around the world to go to major national laboratories, for example, CERN or DESA or other places in Europe. And we believe we found a scheme through the European Research Commission that could actually cover these for 50 students in the first case. Each student would come to CERN or another lab for up to 1 year of training, and all the costs would be fully covered by the EU. We're also working on a possibility that UNESCO may fund some more of these proposals. They'll be very similar to the CERN technical and doctoral student training program, and also to the DOE JIRA awards that were introduced a few years ago. So that's what the panel does. And now on to the Instrumentation Award that we felt was very important to create. So the call for nominations to the community went out on December the 1st, 2021. So the idea is that there's an Instrumentation Early Career Award that recognizes achievements in instrumentation made at an early stage in one's career by an individual or a group of individuals, and has the promise to make or has already made an advance in the field of particle physics. And the early career stage is defined to be 15 years or less from the time of the PhD, properly accounting for career interruptions, career breaks, maternity leave, illness, and things like that. And then there's the Icfa Instrumentation Award, recognizing achievements in instrumentation by an individual or a group of individuals that have made an advance in our field. And the award recognizes a technology development, for example, in the past was the bubble chamber and the multi-bubble propulsion chamber, and or can also recognize a contribution like that, but in addition, a contribution also to community organization, training, outreach, and technology transfer, but not in isolation. It must be with a technological development as the primary part. And so the process involved the community nominating people. There was a request for a CV for each individual included in the nomination, a list of the most important publications pertaining to the nomination, and at least 2, and no more than 3 supporting letters. And then the nominations that we received, and there were many, really, truly outstanding nominations of superb scientists, they are active for 3 years. So there's no need to resubmit a nomination for a following year. And we recognize that we are diverse, that we're global, and so the nominees should reflect that diversity. And so we ensured and advertised and encouraged support from the community to identify underrepresented groups in our field and make sure that they were also represented in the nomination pool. So this is the second half of the message that went out to the community on December 1st, signed by Stuart Henderson, who is one of the directors of Jefferson Laboratory in the US, and is the chair of Icfa at the moment. And it was signed by the whole of the Icfa panel, and also by our panel as well, our sub-panel. So this is the award committee. So the 16 pictures here are the 16 members of the Icfa Instrumentation and Innovation Panel. And they are the people shown here. They're all well known in the field. One of them is sitting right at the front, Francesco, who played a very important role in helping to manage all of the machinery that enabled us to make the selection. There were 7 additional experts added to this panel because this is a great panel, but it's not very diverse. And so we added 7 additional members, Atsuka Ishikawa, Roxanne Gwinnett, Anna Emilia Machado, Giuseppina Bisogni, Laura Baudis, Raja, and I can't see the name. I can never say her name, but I always manage to get it wrong. She is a fabulous physicist from Morocco, and Elisabetta Barbero from Australia. So all these people come from across the world, and they represent, with this group, a panel that we felt was diverse. 9 of the 23 members of the committee were female, and representing every continent on the planet. So when you have a nomination, you uploaded it to this Indico site, which remained live until the 21st of January, 2022. And then we made the selection procedure. So on that day, the nominations closed for both awards. We had astonishingly high-quality nominations, which meant that the task of the committee was extremely difficult indeed. All documentation was ported from CERN to a secure site in Pisa and accessed by the committee via a Google Drive that was password protected. And that documentation was circulated to everyone on the 30th of January. And then over the following 10 weeks, the committee made its deliberations. Every candidate's nomination was very carefully read and ranked by each committee member, and each nomination was discussed in the committee itself, face-to-face. Members of the community not involved in the nomination were contacted by the committee to determine, is there a compelling evidence that the main contributions were made by the nominee, or were there other people that perhaps also helped? In which case, if they helped as well, is there a reason why we should only pick this one person to receive the award rather than more members of the community? And also we asked the question, have there been developments in the same category of technologies by others that should also be recognized by this award? And if so, should that happen now or should it happen in the future? And so all of that occurred over that course of 10 weeks. And then after 2 rounds of rankings and 2 committee meetings for each award, so that's 4 rounds and 4 committee meetings in total, the 2 awardees were determined. And the results were reported to our Icfa panel, who ratified them in April, and then the results will be announced today at this meeting. So now we're going to get ready for the announcement of these awards. So I think Francesca's going to help me with this bit here. So as I say, there are 2 awards, and the choice of whom was really, really difficult. Many of the people that were nominated are very eminently worthy of the awards and may well win the award in a future year. But of course, we have to make two decisions. And so we chose 2 truly outstanding candidates. So the first is one of the most exciting young people in our field today. And so the person who has won the award is Claudia Nones from CA Saclay, the 22 Icfa Instrumentation Early Career. So Claudia.
Commemorating this award.
Thanks for that.
Thank you so much. Congratulations. And now we move to the Senior Award. And in this case, the candidate could not be with us today in Pisa. And so he's online, and I hope that he's going to be able to hear what we're now saying. So the Senior Award goes to Valko Radica of Brookhaven National Laboratory. Valko, can you hear us?
Yes, hello. Hello, Velko.
Well,
Oh.
Hello, Volko.
thanks the
So-
committee. I appreciate most what you are doing, and also for the young scientists and the new generation. And threads have one important function. And of course, I remember the PIsa meetings that I've attended in the past with great pleasure. I would like just to give a short message to the young colleagues. I think we can succeed in developing your careers in instrumentation as much as you concentrate on a single subject in obtaining a PhD. You will do best when you broaden your interest to various fields of instrumentation, which is very diverse, from the physics principles of detectors to various techniques in instrumentation. Thank you very much.
Thank you. There's one more group of people to thank, and that are the 23 members of the selection committee. Francesco in particular corralled and organized so much of this work that made my own job as chair extremely easy. So I want to thank all of them, but especially Francesco. Please join me in a round of applause.
Thank you, Jan. Thank you, everybody. I'm extremely proud that we have been able to award the first edition of this prize at the PIsa meeting, which is a long-standing instrumentation conference. I think that's been very, very exciting. So both Claudia and Velko will give special talks, Claudia on Thursday morning and Velko on Friday afternoon, just to outline their research and give us a feeling of what's in the future in store for us. And I think now it's time for the coffee break, and so we'll stop now and we'll reconvene at 10:40, okay? Thank you very much, everybody, and thank you, Velko and Claudia.
So please take your seat because we should start in time, having accumulated already 20 minutes. Please, if you want to have lunch at the right time.
Nice. Yeah, anyway, you need to wait. So like, you start at 5 minutes before the end or 3 minutes? I don't remember. You start at 5 minutes? Yeah, sure, but when did you show me the first reminder? That will be 3 minutes to 8 minutes, so that's half. Yeah, you should not panic, yeah, once you see the midterm. 8 should be, yeah, okay. I signed for 400 people, you know, I signed for 400 people. I won't start before there is at least 300 free. Yeah, sure. Yeah, but they should have loudspeakers in the coffee area, retransmitting what we're saying. Yep. Mm-hmm. Yeah. You should have a rain planned right just before the session starts. People will get in.
Okay, please take your seats because we are starting now. Again, good morning to everybody after the coffee break. This section is the Detector System and Future Accelerator session, and it will be chaired by me and Dave. Actually, Dave will start, and at the end, still Dave will give a short summary of the poster which you saw in the other room. Just let me say one word because I came from PIsa, so I'm very much pleased to see so many young people this year at the conference. It really gives the impression that our field is still very alive and kicking. And I must say that I was very much moved by the word of Ian, which was inviting us of the older generation to, let's say, don't betray the young people. So I agree, but I also make an invitation to young people, please betray us, because we saw many nice words and a reminder of concepts like gender, bias, diversity, minority, which are extremely important, but The thing, to my view, which is to be most protected is the creativity and the energy of youthness. And I wouldn't like that we create a generation of people who are scared about the future. So respect and study the past because it's important, but create your future because it's you that will live the future, not us, fortunately. So, Dave, please.
Okay, hello. I'm slightly scared about the future of the agenda, so let's go on quickly. So we have Jérôme Bordeaux from Strasbourg, who is going to tell us about the Bell 2 upgrade program.
Thank you for the introduction. Good morning, everyone. Thank you for the organizer for setting up such a beautiful scene and also technically superb meeting, and also inviting my experiment, Bell 2, to report on its upgrade program. And as you may spot here, I've put a capital S here because we have various timescale, we have various technologies, of course, and then in the first part of my talk, I will review what is the status of our experiment and the rationale for which we're thinking about these upgrades. Then in the second part, I will give a quick tour somehow of the numerous proposals, both technological and also R&Ds that those upgrades are pushing forward. So let me first remind you that both the collider, SuperCakeB, and the detector, Bell 2, are major facility of particle physics today. It's not only a bee, but also a charm and tow factory, which initial physics program is based on a large, enormous amount of integrated luminosity at a modest center of mass energy, so one of the epsilon 4s. You can find this our initial program here. And to reach this massive amount of data, we of course need an extremely high luminosity collider at the frontier of the intensity, as we say often. That means we basically need a peak luminosity will be in the multi 10 to the 35 per centimeter square per second range. SuperCakeB plans to achieve this with high current with the so-called nanobeam scheme, assuming as well specific crossing features for the two beams. And this is, of course, generating a very high rate, which in itself is a first challenge, but also quite a challenging background conditions. This is a picture of the accelerator, collider. I will skip it quickly and focus on the Bell 2 collaboration first with now, which has grown over the years to almost 1,000 researchers. And especially, I mean, this detector grow out of Bell essentially to match two challenges: the lower boost, which is requiring for an improvement of the vertex, as well as I mentioned before, higher rates and radiations level. So this is Bell 2 today. This is a standard, let's say, setup for at a collider with inner layers, the Vertex Detector, made of two different technologies, depth and double-sided silicon strips, about which you will hear or can look at a poster tomorrow from Christian Irmler. Then we have our main tracker, which is a central drift chamber, made of almost 60 layers with diverse density over the radius. Then beyond these two tracking devices, we will find specific detectors for particle identification, namely the time of propagation detector and the aerogel ring imaging Cherenkov detector, which will be both presented during talks and poster in this afternoon session. Beyond that, we have an electromagnetic calorimeter, cesium iodide doped with thallium, and, well, a magnet, of course, and then the K-long and muon detector, essentially made of resistive plate chamber with a few layers using scintillators and CPM. So that's the present detector. And how good are we doing with respect to luminosity? This is the profile of the integrated luminosity with time. Here we're starting in 2019, and we are today. This I got from yesterday, yes. You see that we have almost accumulated 400 inverse femtobarn. And just the past 2 weeks, I think, we again break the luminosity world record with just slightly higher than 410 to the 34 centimeter squared, minus 1 second per second. So, of course, with time, we will grow this luminosity, and that will call for, in fact, a few shutdowns. So the first one is driven by the experiment itself. Bell 2 needs to complete its status and to get more robust. I will say a few words about that in a few seconds. So this will happen basically now, in the coming year. And with that apparatus, we will reach with the present collider 2 times 10 to the 35 or so. Then, driven by the collider and to reach higher luminosity, there will be another long shutdown around these dates, 26, 27, where most probably the interaction region will need to be changed. And we will see what are the consequences. Finally, we already have some ideas beyond 2030 to extend the physics program with much higher integrated luminosity, possibly times 5, and although having polarized beams. So for us, the motivation for upgrading means that in any case, we need to mitigate the impact of the large beam-induced background. We need to increase the detector lifetime against radiation, and in parallel, we always search for improving performances in terms of getting more physics per inverse attobarm accumulating. So, these various, let's say, dates translates into a short, medium, and long-term program, which is affecting diversely various parts of our detector. So what is already either ongoing on plan is what we call the short-term upgrade, which will not be covered, in fact, in this talk. We are completing the second layer of our pixel detector. We are replacing some photomultipliers for our PID device, namely the top detector, and we are also replacing boards for our data acquisition system. It's a midterm. Due to the modification of the interaction region, we think that we will need to do something about the Vertex Detector, possibly parts of the main tracker, and again PID. And in the long term, a lot of Bell 2, of course, will be affected. All these proposals or ongoing activities are reported in our SNOMAS contribution about the upgrade plan. So now I will start the second part of my talk, where I will tour about the various detectors, starting from the inner part to the outer part. And first, the Vertex Detector. So I remind you that this is targeting what we call the medium time scale. And we are proposing upgrades because of the refactoring of the interaction region. So where we try to have a larger safety margin with respect to potential much higher background, and although trying to improve the performance. We are thinking also to being able to potentially cover the inner part of the main drift chamber if there are issues with this highly dense wire area there, and possibly contributing to trigger, which we are doing, we're not doing now. This is the sets of requirements, and I will mostly insist here on the material budget and heat rate. So this E plus E minus collider or experiment is a bit special because we need very low material budget, like let's say future high energy E plus E minus collider, but we have much higher rates than they could possibly have. So as you see, there are various technologies considered. The two first one being the present in the detector already. The strips going thinner and also with a finer pitch in the Z direction. Then the challenge here, because of the thinner sensor, is to get a good signal of noise ratio, hence the new ASIC. And although the depth sensors are thinking about accelerating the readout with a few tricks involving larger gain and reorienting the way the readout is done. And there are two newcomers as technologies, silicon on insulator pixels, which are proposing an original readout architecture allowing for relatively medium-sized pitch, I would say, for this kind of monolithic pixel sensors, and an integration time around 100 nanoseconds. We also have a proposal based on standard CMOS depleted monolithic active pixel sensors in the 180 nanometer technology that we are already experiencing in various experiments. And we are planning to build a new sensor out of an existing sensor developed for the Atlas ITK R&D. With similar, let's say, properties. And in addition, and you will hear about that in one talk and one poster for tomorrow's session, we have a full detector concept associated with this technology. So I will not say too much about it. Moving to the main tracker, the upgrades there are targeting more short and medium term, again to increase the robustness against radiation damage, and although mitigate something relatively specific to the readout channels on the present drift chamber, which is a crosstalk. So they are refactoring currently the main readout board with a new ASIC, including more functionalities, and also considering changing the main FPGA here, which is the current one being more prone to signal event upset. So this is basically happening now in terms of testing and production. In the long term, and in the case that it appears that the inner layer, the inner part of the drift chamber might not be suited to really catch or match for super high luminosity, there is a proposal to replace parts of the drift chamber by a time projection chamber and extend the silicon parts in the inner part of the drift chamber. The TPC being then read quite quickly with grid peaks like micropattern detectors. If I still go upward and reach the particle identification detectors, so both the time of propagation detector and the aerogel ridge, as I said before, TOP is already ongoing in the short term and possibly also in the medium term, a replacement of its photodetectors with using life extended atom layer deposited microchannel plate detectors, and possibly even replacing those with CPM technology. You see in this plot basically both the timeline, and we are here, and maybe, I don't know whether you can read it or not, but the rates that those photo detectors need to sustain. And with here the quantum efficiency. And you see that this 80% here, below which we don't want to get, requires each time to change the technology. We are doing that jump today, and we may need to do this other jump with life extended ALD next time. Of course, reading out the CPM requires also a number of upgrade of the readout part. For the aerogel rich, it is a priori suited well for the short and midterm case of supercake B. So now upgrade activity are focusing on the long term by potentially replacing this the current hybrid APD with CPM or large area picosecond photodetectors. And here you see a sketch of what could be the future detector with the LAPPD. I am mentioning here a proposal, although in the long term, to cover some gaps between the quartz bar of the top with super fast timing CMOS maps sensors. So the calorimetry, just before concluding, is also thinking of an upgrade in the long term, essentially to reduce the pileup from the beam-induced background, and that can go with, let's say, faster signal detection to get a higher or a lower equivalent noise energy, either by replacing the photodetectors from pin diodes to avalanche photodiodes. As you see here, the amplitude is much higher with integration time, or even going to much faster crystal and go to pure CSI. There is also a proposal actually to be sensitive to the photon incident angle, installing a pressure in front of the calorimeter with some sandwich of crystal and silicon pixel layers. And simulations have demonstrated this kind of angular resolution. K-long and muon identification system is also planning a medium to long-term upgrade. Currently thinking about replacing the RPC with scintillators, which require also moving to CPM readouts, and investigating in probably a longer term the possibility to have measurement of the energy of the can and more easily reject neutron background by going to faster timing detectors that are being tested here, and you can see the usual single photon counting picture from the test here. We are also continuously improving the trigger by replacing the main board here used to actually handle the data from the events, and also improving the firmware for various background rejection or better decision making. So as a conclusion, I think we can state that Bell 2 Physics Gold has steered and is still steering quite a rich instrumental program. We are currently operating very efficiently with peak luminosity very close to 10 to the 35, which is already quite a good, excellent achievement, I think. In the short term, we should consolidate our existing technology just to go over these limits, and the medium to long term should allow us to enter safely in the regime of 610 to the 35, possibly even beyond. So in the very near future, what will come is a report from the International Task Force about increasing the supercake B luminosity. This will happen this summer. And for the medium-term upgrade, we plan to have a conceptual design report ready by the beginning of next year. Thank you for your attention.
Thank you very much. Any questions? Yes, I see one here.
Can you be more specific about the sources of the backgrounds that are limiting the luminosity? Is it beam gas? Is it Tushek? Is it synchrotron radiation?
Okay, so indeed, I had planned a slide at least just to remind you what are our various sources of background. So one type or three types of background, let's say, is due to single beam. And I think they are more affecting the the detectors in the out part of Bell 2. I think we have to recognize that especially those two are slightly higher than expected even now. So because the inner layer detectors were ready to face a very large background, because for the inner layers, this will definitely be the luminosity-driven background, which will dominate. So the inner detectors, like the Vertex Detector, is not suffering from these. Okay, but the outer part, we're not really expecting that, and that's the reason why we have now short or medium upgrades to be more robust against these. Then, at much higher luminosity, and this is why we need to think about an upgrade of our Vertex Detector.
Okay, thank you. Any further? Daniela.
Yes, I was wondering about the increase in luminosity, because you're not yet quite at the planned luminosity. When is that coming? And, you know, because everybody's waiting for the bell to,
we too.
for violation.
It will come, don't worry. So, what the machine people are telling us is that the present machine can reach this luminosity, 2 times 10 to the 35. And probably this will be reached after we recommission the collider and the experiment after 2023. Maybe not during the first year, but quite quickly. Okay? So the plan is to have accumulated, let's say, I cannot advance any number, but multi-inverse autobarn before we do this second shutdown. And this second shutdown will happen if we know how to get really a factor 3 or so from that. Okay? So then this is what we can use, and that's why we have an international advisory committee for supercake B luminosity. We should find the best path to reach this luminosity after 2027, and in something like maybe 5 years, accumulate the rest of what we need, the 50 inverse autobarn, to complete our physics program. That's the grand plan.
Okay, I think we're out of time, unfortunately, but I'm sure there will be time to address the speaker later on. So let's thank him again. Okay, next up we have Heinz Penninger, who will tell us about the Atlas upgrade program.
So, first of all, thanks to the organizers for organizing such a nice meeting again after 2 years of COVID. It's good to see everybody here. And I would like to give you an overview of the upgrade program that Atlas runs right now. So, Atlas prepares now, in parallel to the data taking for run 3, for the upgrade, the big upgrade that's going to happen in 2026 onwards during LS3, Long Shutdown 3. And the goal is to prepare the experiment really for all the data taking and physics analysis that will happen from run 4 in high luminosity LHC afterwards. Together with the possibilities of HLLHC, of course, we get quite a number of challenges, in particular on the detector side, electronic side, and data acquisition side, that comes with the increase in luminosity. So we go up in instantaneous luminosity by a factor 5 and 7, and then really the integrated luminosity altogether is up to a factor 10, which means, of course, for the detectors, in particular the tracker in the center, a lot of radiation hardness is required, so new sensors. And with the added hit rates, of course, the finer segmentation of the sensors are really important. We get the increase in luminosity by overlapping all the collisions into a single bunch crossing. So we go up from a pileup of about 50 today to up to 200. And this means pileup, in particular in the forwards and the calorimeters, means very high hit rates in the center of the tracker. And this is all the things that we really now address in the upgrades. Last but not least, to benefit from the high luminosity, you also have to write the data out. This means a complete upgrade of the data acquisition system and, of course, in particular, the trigger system. And this is essentially covered all in one slide now. I try to summarize all the upgrade projects in one go. So you have on the left-hand side essentially the upgrades that are targeting the whole experiment, right-hand side, sorry, that target the whole experiment, which is the upgraded duct, trigger system, electronics upgrades, forward detector upgrades, and then 3 detectors itself will be partially replaced, partially added. So the tracker will be completely replaced. Then around the solenoid, we will get new muon chambers, and in the forward direction, we will get a new detector, timing detector, the high granularity timing detector. And over the next slides, I want to give you at least a snapshot of all of them. You can find many more information in the posters. So, starting with the tracker upgrade, the present inner detector will be completely taken out and replaced by a new detector. This is primarily because of radiation damage, but also hit rates and material budget. The goal is to have a tracker that has per track approximately at least 9 data points. So here you can see the average number. And the second important goal is to really extend the tracking capability now to a broader rapidity range. So instead of going from 2, where it currently drops off, we work on getting all the way up to 4. Now, one very important part, in particular for the calorimeters, is the material budget. So here you can see the material budget of the present tracker, and this is the goal for the future tracker, and attention on the scale. So it's really a factor 2 improvement, despite all the technical challenges. So where do we stand with it? Starting inside out with the pixel detector. Of course, one of the core of the pixel detector is the pixel front-end chip, and this is being developed jointly with Atlas and CMS together in the RD53 collaboration. So there, the goal is 50 by 50 microns pixel that can essentially grip and deal with all the data rates, even in the very center at 3 gigahertz per square centimeter. We have, after successful prototypes, also now the first full-size chips in hand with the ITK Pix V1. The wafer testing yield, this is averaged over 50 wafers, is actually 80%, which is quite good news. Here you can see the wafers, and out of that we have started building now the first modules, pre-production modules, with 3D sensors for the innermost layers and NMP sensors for the outer layers of the pixel detector. Similarly, the hybridization module program is really now ramping up into pre-production. Of course, the next step is to put it on support structures, and this is work that goes on, of course, in parallel to the module. This is the design of all the carbon fiber structures. And here you can see the first prototypes assembled onto carbon fiber support rings, then integrated cooling services. So we're really making the step now towards the oval detector. Moving on to the strip detector. So the strip detector is excuse me, a total of 18,000 modules, so 170 square meters of NMP sensors together with 3 different front ends that sit on a single hybrid. So here you can see a picture of an end cap module. The sensors are all in production now, so these are some example measurements of the collected charge as a function of voltage for irradiated sensors. So these lines here are essentially the maximum that we're going to see. And over the last years, the whole module program is now going on quite well. Here you see the strip module, irradiated modules. So this is a plot of showing the noise occupancy and the efficiency as a function of threshold after full irradiation. So you can see after full irradiation still a very nice operational window. And of course, in parallel, the whole mechanics follows up now here with an assembled pedal. And this is the support structure actually for the end caps that will hold these pedals. Moving on to the high granularity timing detector. So this is a complete new detector for Atlas. The goal is really to help pile-up suppression in the forward direction. This is where the tracker alone cannot really help a lot anymore because of the decreasing impact parameter resolution. And this is where the timing and the association of tracks to a primary vertex using the timing really helps. This you can see in this plot here from the HDD DDR. what is needed is a time resolution of around 30 to 50 picoseconds, and this is achieved with LGAD sensors. The LGAD sensors, low gain avalanche detectors, really use charge multiplication to achieve a very high timing time resolution. This is a lot of development that has been done both by Atlas CMS as well as in the Audi 50 collaboration, and with the latest sensors, which actually use carbon-infused silicon, we can lower the operation voltage while achieving still the same multiplication that essentially other detectors can do, but at half the voltage. Here you can see the time resolution, so at the level of 300 to 400 volts, you're already at the time resolution about 40 to 50 picoseconds. So the first modules are being built now with that, with the Altirock chip. So the second version of the Altirock chip is available and goes through all the electrical testing now. Moving on to the calorimeters. So first to start with the electromagnetic calorimeter, the liquid argon calorimeter. There the detector itself will remain unchanged. So this will stay in the experiment as is, but the entire front-end electronics chain and back-end electronic is going to be replaced. So this is actually was a two-step program. The trigger part of that was already replaced in LS2 now for run 3, and for the LS3 upgrade from 26 onwards, all the front-end chain will be replaced. In the front-end chain, the goal is to have a 0.1% linearity all the way through to 300 GeV, and digitize all the waveforms for every bunch crossing at effectively 10 bits resolution to be able to reconstruct then the energy as well as the time, the arrival time, out of the digitized waveform for the entire calorimeter. This altogether brings us to a quite big 300 terabits per second overall data transmission from the detector. In the hadron calorimeter, in the Untitled Cal, we again have essentially the detector stays as is, with the exception of replacing a few PMTs, but the entire front-end chain will be newly developed. This is with the Phoenix board and the what is called main board and daughter boards inside the drawer system in the existing space for the electronics on the detector. Again, the goal here is, of course, to improve the access maintenance, but also provide a fully digitized readout to the data acquisition and trigger system afterwards. This is now in pre-production, has started, and these are some example tests from test beams that run in parallel on the detector. More of the electronics will then be covered also by Francesco's talk on Friday, actually, in the electronics session. Muon detectors. So the biggest part of our muon detector increase or upgrade was, of course, the new smooth wheels, which were installed now. But also for LS3, we're going to replace the inner parts with new small MDTs, RPCs, and TGCs. The goal of the replacement is really to bring up the, the trigger acceptance back from what it would be with the present detector at high lumen LHC to essentially 100% or close to 100% over the barrel part, essentially rapidity of 1. Here the MDTs, the small MDTs are already in production, and the RPCs, chip and TGCs are essentially in the pre-production stage now with the first prototypes being constructed. Good, brief update on the forward detector. The forward detector focuses, of course, strongly on the luminosity measurement, which in Atlas is being a combined measurement from a diamond detector as well as will be in the future from a pixelated devices. They're both inside the ITK, and then we have a dedicated luminosity detector, the Lucid 3 detector, which is a Cherenkov detector. Good. To benefit from all that, new detectors, we are going to have an upgraded duck and trigger system as well. The most important upgrade is, of course, the increase of the level 0, the lowest hardware readout, from 100 kilohertz to 1 megahertz, but also a 5-fold increase in latency, which means a lot of on-detector storage. And then here you can see a sketch of the parallel path of the data, all running from the Phoenix all the way into an event farm, and the trigger, which is largely calorimeter and muon based in Atlas, running in parallel, providing within 10 microseconds a hardware trigger to the overall reader chain. Prototypes of this whole chain are essentially in construction. Part of them already are in operation now since LS2 for round 3. So, if you want to know more details, on this slide I listed all the various posters, mostly posters. You also have a presentation from Laura tomorrow on the ITK and from Francesco on Friday on the electronics upgrade. If you want to know more, I invite you to have a look at the posters. So to summarize, Atlas is really running through now a pretty large upgrade of its detector, electronic and data acquisition systems to prepare for high-lumi LHC. We're going to have a 5-layer new pixel detector, a 4-layer strip detector in the ITK. The first time a high-resolution timing detector for pileup suppression. And of course we get an upgrade of the muon detector together with a full upgrade of the electronics for the calorimeters. Thanks very much for your attention.
Thank you very much, Hans. Any questions? Yes.
Thank you for the nice presentation. What is the strategy regarding the timing detectors, regarding the acceptor removal and the corresponding inhomogeneous gain change?
It's so, as a background, the L guards in the form that I showed here essentially will run up to a radiation level of 2 × 10⁵, 2.5, maybe 3. So this is what the technology can digest at the moment. This is good enough for the outer radii, so the detector goes essentially up to 1 meter. So for the outer radii, this will be installed once and forever. The inner radii, there are two rings, 2 concentric rings, they will be replaced essentially. Whenever this is meant for the middle, what is called middle ring, a replacement roughly after 2 inverse autobahn, and for the innermost layers, maybe 2 replacements actually. So at the moment, with what we know now, the strategy is keep the outer rings and replace the inner rings when necessary.
Okay, thank you. Any further questions? We do have time. Everything is completely clear. Remarkable. Well, let's thank the speaker again. Okay, next up we have talk about Auger.
So yes, hello everybody. Yes, I'm going to present, also in this case, an upgrade, the upgrade of the Pierre-Auger Observatory, of the Pierre-Auger Observatory. But of course, I want to introduce before starting the Pierre-Auger Observatory in its baseline design, as it was in the last 15 years of data taking. In particular, the Pierre-Auger Observatory is the largest detector for the hybrid measurement of cosmic ray at ultra-high energies. In particular, it's formed by a sparse array of water Cherenkov detectors on a grid of 1.5 kilometers, plus 24 fluorescence telescopes for the measurement of the fluorescence radiation in the atmosphere that are overlooking this area of more than 3,000 kilometers square in 4 buildings that you can see in this picture. Plus, during the lifetime of the observatory, several enhancements were added to this baseline design, with a denser array in the area near the Koyo Echo telescope and 3 more telescopes to overlook this area with an higher elevation, plus engineering array of underground muon detectors for the direct measurement of muons of the showers, and also an engineering array of radio antennas for studying this kind of new measurement for the showers, ultra-energy showers. So it's important to underline that all these detectors are tested, always tested, for the harsh environment of the Argentinian Pampa, with high temperature excursion during all the years and also daily, strong winds and a very dusty environment. During the lifetime of the observatory, with more than 15 years of data, of course there are several results, very important results, both on the flux of the ultra-high-energy cosmic ray, with the establishing the suppression at the highest energies, and the study of the mass composition at the highest energies up to at least 10 to the 19.5 EVs. Of course, also with this data, new question arises, particularly I'm reporting here the origin of the suppression is still not clear, and also this will be pretty answered by knowing the composition of cosmic ray at the highest energies that up to now was not possible to study because of the limited duty cycle of the fluorescence detectors that of course can function only in clear and moonless nights. Then other question of course arise that the most important is the origin of the ultra-high energy cosmic rays, so the sources of these high energy particles. Of course there are several results coming from anisotropy both on large scale, thanks to which it was possible to understand that the cosmic ray above 8 eV more or less should be of extragalactic origin, and there are several hints of correlation with precise sources, mainly AGNs and Starbucks galaxies. But still, the quest for the sources is open. Plus, coming from the difference between simulation and data, the muon puzzle, so the missing part of the muonic showers with all hadronic models. So for this reason, and also other open question, the upgrade was founded and started its deployment. In particular, the main goal is to understand the mass composition at the ultra-high energies, in particular in the region of the suppression, in order to understand the origin of this feature of the energy spectrum. For instance, in this case, we can see in the lower plots how with the Auger prime upgrade, it would be possible to distinguish different scenarios that up to now cannot be distinguished due to the low statistic of fluorescence detector. It will be possible to study the anisotropy with the new information from the chemical composition, and of course it will be possible also to study the interaction in hadronic models at the highest energies that cannot be reached in accelerators. And with the improved performances of the electronics, it will also be possible to better estimate the gamma ray and neutrino fluxes to be used in future experiments. So now I'm going to sketch the several detectors that will be added in the upgrade, in particular a scintillator detector in the upper part of the tank, mounted over each water Cherenkov detector of the array, and also a radio antenna that will be mounted for each water Cherenkov detector, an underground muon detector, a scintillator that will be put below the water Cherenkov in the denser array area, and a small PNT in each water Cherenkov to increase the range of measurement of the tank. All these detectors will be read by a new electronics that will also increase the performances in general of all the channels. So going to every one of these detectors, the scintillator surface detector is formed by 48 scintillator strips that are read by wavelength shifting fibers, and all that read 2 bars at the same time, and so the 96 ends will be bundled and read by a PMT mounted in the tube that can be added also at a later time and easily maintained. So the production of all these modules is already finished, and all the modules are installed. The PMTs are going to be installed together with the electronics in this very moment, but a pre-production array of 77 of these modules is already in the field and taking data since March 2019, and so a first long-term performance study of this new detector was already presented at the last ICRC. In particular, the aim of the scintillator is to measure differently from the water channel of the different particles, in particular the electromagnetic part with respect to the muonic part, and so to be able, thanks to the difference between the two signals, to disentangle the two components of the shower. A similar work will be done thanks to the underground muon detector that, being put 2.3 meters underground, will allow to completely shield the scintillator from the electromagnetic particles, electrons and gamma, and instead directly measure the muons of the shower. Also in this case we have scintillator, 64 strips that are read by a wavelength shifting fiber also in this case, and all the fibers are bounded and read by an array of silicon photomultipliers. In the end, there will be 73 positions in the denser array area, where there will be 30 meters of detector. In particular, each module will have two acquisition mode, a binary mode to count the single muons, or anyway a very low numbers of muons, where each trace is handled separately by the FPGA, and an acquisition, an ADC mode, in which all the signals from the silicon PN are acquired and analogically added to measure higher densities of muons. Then there will be the radio detection, so in particular, the great improvement that will be offered by detecting the radio signals from the shower will be that in the case of inclined showers where the electromagnetic particles are absorbed in the atmosphere, it will be still possible to measure these, to have an indication of the electromagnetic part of the shower thanks to the radio emission. And while the muonic component will be measured by the water Cherenkov detectors. The radio upgrade, the radio detector, will be formed by putting one dual polarized short periodic antenna of 1.2 meters above each water Cherenkov detector, and in this way it will be the largest radio detector for measurement at the highest energies in this moment, in particular with an exposure that will enhance the exposure of the observatory for the horizontal events. Finally, also a small PNT will be added inside each water Cherenkov detector. This is a 1-inch diameter PNT with respect to the 9-inch PNTs, 3 9-inch PNTs that are already inside the tank. In particular, it will be supplied by a dedicated module that was in particular tested to have a high resistance in the harsh environment of the Argentinian Pampa. And thanks to the very different area, of course, of this small PNT with respect to the other PNTs that in fact are called large PNTs, it will be possible to measure very high densities of particle, where usually the large PNTs were saturating, initially with an electronic saturation, so an overflow of the FADCs, and then with a going out of linearity. Instead, with a very different area, it will be possible to measure, to properly measure up to few hundred of meters from the shower core, and so to have a very high resolution in the reconstruction of the LDF and so of the energy. All these new detectors and new channels will be read by an upgraded electronics that, of course, has to read all this channel to interface with the underground muon detectors and the RD antennas that have their own dedicated FPGAs, and then also doing the data acquisition and transmission to the central data acquisition center via radio. The new electronics, of course, is backward compatible with all the cables and all the channels and PMTs that were already inside the tank, but it will have faster ADC, 3 times faster ADCs, a larger dynamic range from 10 to 12 bits, and upgraded CPU and FPGA. So to handle all these new signals and to improve the performances, in particular for the trigger part. Also in this case, it's very important the manufacturing of these UUBs that completely, of course, in practice have to handle all these tasks in the difficult environment of the Pampa. So there is first a manufacturer test of the Citadel company, and then an environmental test in which the UUBs are stressed, in particular in temperature, and which with turn off and so on, to be sure to be resistant in the Argentinian Pampa. Then with all these new detectors, it will be so possible to for each single shower to measure many more observables, and in particular have many more measurements both in the vertical part, so up to zenith angles of more or less 60 degrees. In particular, in this case, the main part will be comparing the water Cherenkov and scintillator signals that have a very different response to muons and electromagnetic particles. And at the same time, it will be possible to add many observables of the radio part, so several observatories related to the slope and the wavefront, but also compare all these information with Monte Carlo, so with top-down analysis, and in the lower energy part and with a lower statistic, also the results from the UMDs. For the vertical part, that was very difficult to analyze with the baseline design of the observatory, instead it will be possible to have also in this case a discrimination between the electromagnetic part that is related to the radio emission and the muonic part from the water Cherenkov detector that is still sensitive also to very inclined angles, and at the same time also in this case for the denser part of the array have the information from the UMDs. In conclusion, with this upgrade, the Pieroget Observatory will gain a high sensitivity to composition, in particular for the highest energies, and it will maintain, let's say, it will have anyway an exposure largest than any other experiment for the ultra-high energy cosmic rays, at least for this decade. The deployment is underway, and it should be concluded and commissioned by half of the next year, at least in its main part, and of course it will give many important information for future experiments, in particular with all the information that we can gain from each shower, as is reported in this beautiful event, if I can, in which all the different detectors can participate and measure the same event, giving all the information to obtain indication on the mass composition. Thank you very much for the attention.
Thank you very much. Any questions? Yes.
Okay, now, what really counts in the composition of the primary is the fluorescence detector, as you showed at the beginning. But that is not affected by this upgrade, because you still have the same problem as usual of you don't widen it. So how does it really improve at high energy?
No, the point is that thanks to the different in a sense, okay, of course the fluorescent detector and so the measurement of the maximum of the shower is the main observable to do mass composition. But another very important observable is the comparison between the two components, the electromagnetic and muonic components, because of course in this case for heavier primaries we have a much larger component of muons, and so this will be the way in which the two the composition will be made, comparing, as in the case for vertical events, comparing the muonic and electromagnetic packet, and so obtain the percentage of the two. In practice, an N-mu versus N-E method.
But you still we will be limited by the fluorescence detector, which gives you the input, because your data does not agree already with simulation. So the model does not correspond to what you see.
The model does not correspond, but of course we can obtain also from, in general, we can obtain indication, even if of course they are not in agreement exactly with the model, but we can distinguish between different scenarios in which there are different components of primaries.
Okay. Well, we can discuss later offline.
Sounds like a good debate for later. Yes, a question at the back.
Congratulations for the very nice talk. Can you provide some information about
Can you speak a little louder?
Yeah. Can you provide some more information about the trigger sim, especially for the antennas? They will be self-triggered, triggered by the scintillators?
No, sorry.
Because I know it's very difficult to trigger the antennas.
That's true, and in fact, at least up to now, all the new detectors are triggered by the water Cherenkov tank, are in slave mode. In particular, for the radio parts, you need at least 3 antennas with affluence and energy fluence above a certain threshold that can be, of course, changed, but those are triggered anyway by the surface detector. Also, the scintillator and the UMD are all triggered. Of course, there are studies about new analysis in which there are triggers directly from this detector, but are still not in the field.
Okay, any further questions? I have one actually. Can you remind us, you talked about the extreme conditions. Can you remind us what the temperature is that your
Well, usually the temperatures in the Argentinian Pampa can go from several degrees under zero, from minus 15, minus 10, up to 40 degrees, of course, during the year, while during each day there can be excursion up to 20 degrees or even more in summer. In fact, there are several, for instance, for the SSD, that is, of course, being up on the upper part of the tank is very exposed to solar radiation. There is a corrugated rooftop to also try to have a passage of air and so lower a bit the temperature of the scintillator. So this is the main, and also for the scintillator in particular, the long-term performances are very important also with respect to the winds, because being mounted on the upper part of the tank, it was verified that it can resist to these strong winds and dusty winds that can be on the tank.
Okay, thank you. Right, let's thank the speaker again. And we have a change of chairperson. Here are the ceremonial articles.
Thanks. So the next speaker is Oscar Augusto de Aguiar, which is going to speak about microchannel CO2 for silicon detectors. Please.
Hi, thank you very much. So today we'll talk about the microchannel CO2 cooling for silicon detectors. And if you're interested to see the dynamics inside the channels, you can open the PPT-X in the website, and then you see the bubbles traveling through the channels. And this was actually a video that was recorded with a high-speed camera. So here you can already have an idea about the structure of these microchannels. So in the beginning, there is a narrow region, which is called restrictions. I'll come back later to this. And then you have the main channels where any power that you put on these cooling structures is absorbed by the liquid CO2, then transformed to gas. So first, I'll give a very, very brief introduction about the VLO upgrade with focus on the cooling part. So this is a cross-section of the detector. So we have 2 modules, one on each side, which is located around the beam line, as you can see here. And the key features are the ones that I mentioned here. So the closest distance with respect to LHC beam was reduced from 8.2 millimeters to 5.1. It also has a very high and non-uniform radiation. And overall, the active area of the detector is about 0.2 millimeters squared. And if you'd like to see more information, you can see the poster that was prepared by Gianluca, which is just outside now. Just a few more words about the cooling requirements. So the requirements for this detector is that the maximum temperature at the tip of the sensor should be below minus 20 degrees to mitigate radiation damage. In addition to this, this detector operates on the vacuum, so cooling is crucial. And on top of all these previous items, we also have the retraction of the cooling by 5 millimeters in the innermost region to reduce even further the material budget contribution. So overall, we have approximate power dissipation around 30 watts per module. And in the sensor area, you have a power density around 1 watt per centimeter squared. So here you can see the modules around the beam and the area which corresponds to the LSB acceptance. So the whole material budget coming from the module matters. So now a few words about evaporative cooling. So here you see another representation of the microchannel that I showed before, with the restriction in front of it, and then the main channels where you have the mixed phase. So the main idea here is that the heat produced by the electronics absorbed by the liquid part that transform into gas. And one curious factor about this kind of system is that since you're talking about evaporative cooling, the coolant decreases in temperature from input to output. And for this cooling, we decided to use CO2 as a coolant because it has a high latent heat, low viscosity, and is also radiation hard. And here I would like to just provide some parameters about this coolant. So the lowest operational temperature is defined by solidification, and this is a paper in which they managed to achieve a stable operation at minus 47 degrees at the cooling plant, just to give you some feeling about the range of the application of this. And on top of it, I also should mention that since you're using CO2 in B phase, then this means that in normal operation, we have a high pressure in the system that minus 30 degrees around 20 bars, and at the room temperature, the pressure is around 65 bars. So this means that these cooling plates need to be validated to a very high pressure, as you can see here, after adding some safety factors. Now I'll focus about the microchannels into silicon. So the main advantage is that there is no CT mismatch with respect to the silicon detector. It also has low and homogeneous material budget. It's also very radiation hard, and also provide excellent cooling performance. So usually this is represented by the thermal figure of merit that you can see here, which is basically the difference of temperature divided by the density of power. And here I put a cross-section of the module, so you can see the microchannels in the cooling plate here. The yellow part is representing the glue interfaces, and here you have the hybrid sensor, which is overhanging by 5 millimeters. And on the top, you can see the two cooling performance plots. The first one, which was obtained with the prototype, in which we estimated the delta T using the power expected in the end of the lifetime of the detector. And then we obtained this variation of temperature of around 6.5 degrees for the tip of the sensor that's overhanging. And on the right, you can see another plot showing the thermal figure of merit that I mentioned before, as function of glue thickness, but now this time with the modules which were produced for the Vela. And this was obtained using the temperature which was measured at the level of the ASIC, so more or less this region here. So the main challenges of using this kind of technology is the production and cost, which there are ways to mitigate them by using alternative techniques for the manufacturing that I mentioned in the end. And there is also the potential of reusing those cooling plates, as was shown for the N62 in this reference here. And in addition, we also have the cooling integration part, which I'll mention later. And it also, these kind of structures, they are more fragile than more conservative approaches. But our experience during production was really good working with them. So this is the layout of the microchannels inside the silicon plate. So this is the silicon plate, and inside you have a racetrack-like design, which was embedded in a 500 microns thick silicon cooler. And here you have some images showing the transition from the restriction on this side to the main channel on this side. And you also have some close-up pictures in the input of the channels that you can see here. These are the input holes and the restrictions inside, and in the output where the CO2 is coming out of the system. So in total, there are 19 channels, which are approximately the same length, around 30 centimeters, and every channel has its own input and output. So I'll summarize very briefly the production of this plate. So initially, it starts from a single wafer of silicon in which the pattern of the channels are etched. Then a second wafer is bonded on top of the structure to close the channels inside. Then this assembly is thinned down to the thickness that's desired. Then metallization is applied in one of the sides that will allow the integration of the cooling connector to the microchannel. It also allows us to put some alignment marks for the assembly procedure. Then the inlet and outlet holes are etched. And then these structures are put in UV tape, as we can see here, for transport. So the first thing I'd like to mention is the resistance to high pressure. So throughout the production, the wafers had high pressure samples, as you can see here, and also the main coolers in the center. And this is one of the plots that were obtained checking the resistance to high pressure as function of the channel width, since these samples had different channels width to be tested. And here you can see the representation of the nominal channel width for LHCb and the highest pressure that these samples were tested. But here there is a remark that neither of these samples showed any type of fracture. And we also checked the bonding based on image which were obtained using a scanning acoustic microscope, as you can see here, in which was quite challenging to try to look for structures like this one. Even changing the contrast and brightness, it was not straightforward, so we developed an algorithm that could run on top of these images and make them much clearer, as you can see here. And based on the location of this imperfection, we tried to divide them in 3 different grades. Grade A, when we didn't see any imperfection, like this one that you can see here. Grade B, where we could see imperfection in the region of the input and output, as these 2 examples. And grade C, when these imperfections were in between channels or just connected to one of the channels. And in total, based on the total number of plates that were delivered, 70% more or less met the grade A quality. So this, the connectorization was actually the most challenging part of the whole R&D procedure, because we also had to use a fluxless process to avoid long-term corrosive effects in the cooling system. So the strategy was first to apply a solder preform, as you can see here on the silicon, do a thermal cycle to melt this solder foil, do this something similar to the connector side as well, then align both parts using a system that could self-adjust, as you can see here. And this is a cross-section of the attachment of the connector, indicating the metallization on both sides, on the connector and also on the silicon side, and the solder in between. And then after this step, we would have the final object that looks like this, with the silicon plate plus the fluid connector. And once we have this object in hand, then we had to do the quality control. So we performed high pressure tests up to 186 bars, plus helium leak tests, initially with vacuum side. We also double check the quality of the joint using a very precise X-ray tomography, as you can see here. And if you, I'm not sure if everybody can see here, but in the PPTX, you can even see the restrictions inside the cooling plate, which are 60 by 60 microns, using this technique. And then we also did a second high pressure helium leak test at 60 bars to look for any inconformities, and we also checked the planarity of the plate after it was processed. And then once this object was ready, then it was initially transported by personnel, by car, or by plane. But then during COVID times, we also had to develop a new system that could be basically a new transport box that could be transported by plane or consolidated truck, as you can see here. So there were no casualties during the transport of those structures. And here you can see an image of the final module with all the electronics already assembled on top of it. And then again, if you'd like to know more information about the upgrade one, you can check the poster. So in the end, we produced 81 grade A, B substrates out of 52 that are needed for the detector, with a yield of 87%, plus additional lower grade substrates. And here you can see 2 pictures just to indicate the status of the detector now. So both halves were assembled and installed at the LHCb cavern, and currently the detector is being commissioned. Now I'd like to say a few words about alternative techniques to build microchannels. So first of all, if you're considering the microchannels embedded in silicon, you could look for alternative techniques like anodic bonding, metallic bonding, and a few other ideas. You could also try to optimize the system in such a way that you can work with smaller cooling substrates to increase the yield of the overall of the production. And there is also a lot of R&D ongoing on new connectorization techniques, as you can see here. So here, just a few examples. I think this one is the most ambitious approach, which is to bring the coolant to the sensor part. So here you see a CMOS sensor in which they showed it's possible to etch the channels inside and then close them with Parlin. And this, if you like to know information, you can check the IDA note. And they also managed to show that using this process, they can build channels that can withhold 110 bars. And there are also other techniques for deconnectorization, which, as I mentioned before, was one of the most challenging parts, in which we can also try to use a 3D mode to basically build the connector already attached to the silicon plate, as it was shown on this presentation here. And on the right side, you see some additional alternative studies about different manufacturing techniques. In this case, they used laser etching with anodic bonding to produce small channels. And this is described on this paper that you see here. So it's also possible to create these kind of structures using 3D printing. And here I'm going to mention more details about one of the possibilities, which is using titanium, which was investigated for the value upgrade, but it's also possible to use different materials like silicon carbide, alumina, among others. And here, the key feature is that overall the material budget is still very low. It's much easier to handle than just the silicon plate. We also managed to show that restrictions can also be integrated in the inlet part. We managed to show that the structures could resist up to high pressure, 250 bars, and they were leak tight if the titanium wall was around at least 250 microns. And the deflections were also below 100 microns. And here you see some images of the structures. This is the overall design of these microchannels in titanium. This is a picture showing these squared pipes, which were 1 by 1 millimeter. However, there were some inconsistencies on the production, like the one that you can see here, that were kind of kinks that were showing up in some of the samples. And here you can see a plot of the cooling performance that was a little bit worse than the ones with microchannels. So for the nominal power, the delta T was around 13 degrees. But on the bright side, it's a production technique that's relatively cheap. So overall, for each module, was actually below 500 euros, including the welding of the capillary for the integration of with the cooling plant, and also has a fast turnaround and production as well. But they also had some, we also had some challenges related to the glue layer, the thermal performance, and these irregularities that I mentioned before. And the last example that I'd like to mention is, which was also investigated for developer grade, was a very conservative one, in which cooling pipes would be embedded in a ceramic plate, in this case chapal, because it's machinable. And here you can see the design of the structures with these very thin capillaries. And we managed to, instead of having restrictions for the stability of the flow, we managed to achieve it using orifices like this one that you can see here. And then we also showed that the thermal performance was also good for this kind of structures. So to summarize, the evaporative cooling through microchannels embedded in silicon has several advantages, such as the minimum material budget, the no CT mismatch with respect to the silicon sensor, and also great cooling performance. The main challenge for the LSB value upgrade 1 was the development of the attachment of the fluid connector. So to reduce the cost of this kind of structure, especially in silicon, alternative techniques are being developed, and we are also looking into alternative connectorization procedures. And of course, in addition, other manufacturing techniques can be used with different materials, and they're also being investigated for the value upgrade 2, which is going to happen in 2030. So we do have a very excited R&D ahead of us for this upgrade. So thank you very much for your attention.
Thanks. Are there questions? One.
You provided us with the price tag for the 3D techniques and also time, turnaround. What is the comparison with the silicon one?
The silicon. So with the large structures that I showed before, the factor is our order of factor 10 difference between the two technologies. But there are also advantages also from the material budget point of view, right? So we have to balance everything out of the simulations and so on.
Other questions? There? Thanks.
I would have a question of the performance. I mean, it was told in other applications that there are problems with the proper location of the saturation line, meaning that the location where it goes from monophase to biphase, and where it starts boiling. Do you have this problem, these issues also in this application?
So one thing that we had to find a solution was the parallel operation of these plates, which we came back to this point. Because so in the end, the solution since, okay, maybe I have to explain in more details what happened. So we tried to operate 2 microchannels in parallel, while powering one, while keeping the one without power, and basically doing the same trick with the other one, and doing cycles of power in these 2 microchannels, and check the robustness of the system. And we checked that then indeed we run to this kind of issues, like one was boiling and then the other one was stopped boiling because the balance of flow was not properly even. So what we did was to install orifices before these 2 modules, and then we showed that if we, on the final assembly of the detector, if we install 150 microns orifices, then this problem was gone. So the whole system was stable.
Thanks. There is another question there. Thanks.
Thanks. So maybe I missed it. What is the minimum material budget that one can achieve without the system blowing up? Like, is it possible to go way below 1% of radiation length? Or, I mean, you need some structural strength to withstand the high pressures.
I think if we can I have the slides?
Sandra?
I think maybe to have one on the backup slides about the amount of material that's needed. So these are the initial high pressure samples that were tested with different designs as well. So we focus on the P4, in which we had for developers. So first of all, it's also related to the design that you'd like to implement. So the first thing that we showed is that if you had large manifolds on the silicon side, this also would reduce the resistance to high pressure as expected because you have a larger area overall. And I think this is the plot, it's the most interesting for the discussion that we have, because here we show that the resistance to high pressure as function of the silicon cover thickness that you can see here. So the amount of silicon on top of the microchannels also depends on the channel width. So here you can see the curve of resistance to high pressure if we have like 500 microchannel width. And this is the one that was decided for the LHCb. So there is still some margin for the optimization in the amount of material, but then it also depends on your choice of coolant. So for instance, if you go for liquid cooling, then you can reduce quite dramatically the resistance of high pressure needed for your detector.
Okay, thanks a lot.
Okay. I have just one quick curiosity. Did you check test other gases besides CO2? Because you explained why it's the best, but did you try something else? For
development rate, we didn't try different coolants.
Just looking at the
just
parameters.
CO2, okay. Yes. But for the future, we are considering to use krypton, but it's still in the R&D phase now.
Okay, thanks. Okay, thanks again to the speaker, and we go to the next talk. The next speaker is Silvia Della Torre from INF in Trieste, which is going to tell us about the design of the Athena detector for the electron-ion collider. Thanks.
Okay. Fine, thank you. So, the Athena is a total hermetic electronucleus apparatus proposed for the electron-ion collider. The first thing to do, if I succeed to change, yes, is to consider the context. Namely, which are the motivation for the electron-ion collider. It is that of the ultimate understanding of QCD by answering to the several open questions that we have about QCD, and here just some major ones are listed, namely full understanding of the nucleon spin structure and its tomography, and the origin of the mass, as well as the evolution of partons, in particularly gluons in high-density nuclear matter and gluon saturation, and so on. And how to do this? By conjugating high energy and high luminosity. And in the case of the electron-ion collider, also enriched with, okay, lost the laser. Ah, here it is. Okay, with a polarized beam. Let me elaborate one moment about high energy and high luminosity. In this plane, in which both scale, energy and luminosity are logarithmic one, please note it, you have what existed or is still at work, namely the only collider here, but also some fixed target facilities. And they are either at high energy but limited luminosity or vice versa. And the new ideas in yellow are all clustering in this gray region where you conjugate the high energy and high luminosity. And among the proposed concepts, one, the electron-ion collider, has been approved. This we learned in January 2020. And together with announcing the site, which is Brookhaven National Laboratory. So this approval went through typical US procedure, CD0, and then later in June last year, also CD1 was awarded, and we are presently here at the beginning of the execution phase. And there are other milestones in front of us, CD2, CD3 that require pre-TDR and TDR, and then to start operation at the beginning of the 30s and completion in 2033. A word about this collider. So it is built in Brookhaven, where you presently have an ion-ion collider, which means that the hadron is dying. The hadron system is already fully present. It will be empowered, while the electron system will be completely new. And of course, you also take advantage of civil engineering, in particularly the tunnel. And for which specification, center of mass energy between 20 and 140 GeV, luminosity up to 10 to the 34, beam polarization, as we have said, electrons and light nuclei at 70% level, but for nuclei, a large variety up to the heaviest, according to Rick at BNL experience, up to 2 interaction region. And important in the accelerator design is the integration of the interaction region, machine and detector to ensure full coverage. And then there is the detector, to which we will concentrate now. So general consideration, of course, the characteristics are dictated by the physics, the QCD measurement that require to study different processes, inclusive, semi-inclusive, and exclusive processes. And each of them has specific requirement in the detector, and here I underline what is very specific to this facility. You need very good detection, measurement, and identification of scattered leptons. Then you need to identify hadrons, reconstruct jet, and find vertex resolution for the decay of heavy hadrons. And when you go to exclusive channels, you need to measure all the particles, elements, tagging the nuclear fragments, and have electron-pion separation at very good level. This has brought to an evolution of the detector concept, starting with the white paper in its 2 issues in which the first ideas were put on paper, and a set of conceptual design followed. They became more mature in 2020 when the whole user group community, presently 1,300 people, designed the reference detector via a robust yellow report. In 2021, we had the call for proposal, and the community cluster around 3 proposals, Athena, Core, and Ecce, with similarities because there was upstream the yellow report, but also differences where the main one is probably the central magnet, a new one with a large bore for Athena, 3 Tesla, new one, a smaller size, 2 Tesla for Core, use of Babar magnet, 1.5 Tesla for Ecce. This process is now over, and in the present year, the groups behind Ecce and Athena are working together to pick up the strengths from the 2 proposals, forming a new collaboration and a baseline detector. The progress is ongoing. What I will discuss today, and which will give you a complete overview of what is needed here, is the Athena detector. To complete this introduction, the complete coverage of the phase space requires not only a central detector, which is of this size, about 10 meters long in Athena, and has a barrel and end caps elements, but you need to cover also these 2 small cones, aperture around 2 degrees, that impose detectors along the beam line in the forward and backward direction, as we will see. I cannot go in all the details of Athena detector, so I will illustrate it by highlights. This is the whole central detector, and here I underline, as already mentioned, 3 Tesla solenoid, that apart a large bore has also very limited material, around 1.3 in interaction length. The other elements tracking calorimetry PID are mentioned in the following slide. Among the highlights is the acceptance. Here you see the geometrical coverage of the central detector, which is really complete for tracking, for PID, and for calorimetry. But this is not enough. The geometrical acceptance is not enough. It is the material budget that tells us where we are. So for the 3 regions, backward, barrel, forward, you see the cumulative material from the interaction point up to the front face of the electromagnetic calorimeter. This material is low, and when it grows, it is only just in front of the calorimeter itself, which a feature that, as it is well known, does not severely affect the electromagnetic calorimeter response. Here, about the tracking, the vertex as well as the barrel tracking and the disk in the forward and backward are with maps, with new maps technologies, fine pitch, low power consumption. These are developed for Alice ITS 3 and adopted here, and complemented for in larger surface, sorry, about with state-of-the-art micropattern gaseous detector. I don't say more because 2 great posters illustrate these 2 systems. In a snapshot, the performances, the fine resolution in momentum, and also that in the resolution of closest distance to the primary vertex. And key ingredients are the high magnetic field, maximizing the lever arm, minimizing the material and the low consumption is essential, and the sensor pitch. This is an overview of the calorimetry, which is really a wide system. In this sketch, you see in blue the hadron calorimeter, in green the electromagnetic calorimeter. A couple of highlights. In the backward, you need the best resolution for the electromagnetic calorimeter, and you get it, as demonstrated in this plot, with classical lead tungstenite crystal of small size, fine pixel. In the forward, you combine electromagnetic and hadron calorimeter in a single bulk setup with a tail catcher for high energy jets. Very interesting is the concept of the electromagnetic calorimeter in the barrel, which is hybrid because you have internal layers of tracking and, of imaging based on the MAPS AstroPix. And then you have sampling calorimeter, but this sampling material, which is lead and scintillating fiber, is already present within the imaging layers. And this allows fantastic separation, electron pion, even where crystal fail at low momenta, and other features as very good reconstruction of gamma zeros. For PID in the barrel, you combine a high performance DIRC, you add focusing elements to the concept of the DIRC, but for low momenta particle that cannot do the path up to there, you have a time of flight layer with AC LGATs, and you have in the forward a D-rich with dual radiator, aerogel and gas, and in the backward proximity focusing rich with very high resolution thanks to an unusual large gap of 40 centimeters. And novelty is the baseline, the use of silicon PM arrays. And this gives you fantastic momentum acceptance for particle separation. The various species are illustrated there over the whole range of the central detector. And when you use also the property of thresholding of Cherenkov, you even enlarge them toward low momenta. Forward instrumentation is classical with fine trackers and Roman pots based on the AC LGATs, while in the backward the main focus is luminosity monitoring, making use of electron-ion Bremsstrahlung and calorimeter setup that can have to work at very different conditions according to the center of mass energy and different luminosities. Okay, this would bring us to the performance of physics. I will just show two examples because time is short. I would like to show you which is the DAS resolution that we can obtain. We use as figure of merit the variable y, and its resolution in the q square x plane, where the size of the dots gives you the resolution and the color, the different reconstruction methods. Another very interesting aspect is this one, that of the fine resolution electron pi invariant mass reconstruction, in particular in the barrel, thanks to the image calorimeter. And that you can find in the slide other example. I go to my summary and perspectives. Here we have reported about the Athena effort. And as underlined, there were more efforts in parallel. This process was over in March this year, and now Athena and Icfa people are at work together to build a new collaboration and a baseline detector one. For the second detector, the time scale is different, And the third proposal, core, can be a starting point for this exercise. We have in front of us the preparation of first pre-TDR and then TDR. And this means a very exciting time that will offer us the possibility to explore all unsolved QCD mystery, and also to challenge us with the preparation, construction, design of great detectors. So there are important opportunities for physics and frontier detectors in front of us, and the door is open to join us.
Thanks, Silvia. Are there questions?
Okay.
No questions? One there.
Is radiation damage no concern at all, in particular for the lead tungstate calorimeter?
Okay, here the situation of radiation damage is of course totally different from that of a hadron-hadron collider, much, much lower. Nevertheless, there are elements for which this is a concern, and these elements are the silicon PMs. The silicon PMs from the, at the moment, from the radiation point of view, are fragile. In this respect, a very robust R&D program is ongoing to compare silicon PMs from different producers and different characteristics, to understand their performance, new, after irradiation, but also after applying annealing cycles, thermal annealing cycles. The situation is very preliminary. There are good indications that this is a direction in which we can move. And the next step is, of course, also that of establishing this annealing cycle in situ, heating the, at the right time, not when you are taking data, the silicon PMs in place. More news in the next future. The work is ongoing.
Thanks. You have a question there.
Hi. Are there specific areas in which more effort is needed? So where do you look for new collaborators?
Well, AC LGATs, definitely. Okay, this because for what concerns the maps, the ITS-3 maps, the collaboration is already ongoing. This is since the very beginning. Also in the direction of AC LGATs, but the path is long. It's not yet well defined in all details. We have to see how it progresses.
Okay, many thanks, Silvia, again. And we go to the next speaker. Okay, we have Massimo Casarza, again from Trieste, which is going to speak about detector design for the next multi-TeV muon collider.
Okay. So I will start setting the context in which a detector at a muon collider is expected to operate, which means basically the background conditions. I will overview the impact of such a background on different detector subsystems and outline some mitigation measures currently under study and showing some reconstruction performance. So the reason why a muon collider is so appealing is that muons are impervious to synchrotron radiation and can be accelerated to several TeV energies in a relatively compact circular machine. Having leptonic collisions at the multi-TeV energy range would enable a tremendous, a very rich physical program ranging from precision measurements of known standard model phenomena to direct searches of physics beyond the standard model. Unfortunately, muons are unstable, so a relevant fraction of the muons circulating in the beams decay. The decay products interact with the machine elements and produce showers of secondary and tertiary particles which reach the detector. Here, just a few decays are represented on the picture. For example, for a 1-point TeV collider, we expect to have 400,000 decays per meter, which result in order of 10 to the 10 particles entering at each bunch crossing the detector. So coping with the beam-induced background will represent the main driver of the design of the detector and the reconstruction algorithms. In our studies, we are profiting a lot from previous measurements and the expertise of our US colleagues of the muon accelerator program. One solution they found and we adopted to reduce the background inside the detector is represented by two cone-shaped tungsten shieldings inserted along the beam line inside the detector, which together with a suitable configuration of the magnets in the interaction region reduce the background inside the detector by 2 or 3 orders of magnitude. They cut out long tail energy in the electromagnetic component of the background, but unfortunately this is not coming for free. The nozzles have no negligible volume, and they limit the acceptance in the forward and backward regions of the detector. Despite the nozzles, a huge flux of particles is entering the detector, mostly photons, neutrons, and electrons, positrons. The main characteristics of this beam-induced background inside the detector are very soft momenta, a few MeV on average for the electromagnetic component and half a GeV for the hadronic. This is an atypical background, is not produced in collisions in the interaction point, but is intrinsic with the beams and enter the detector along the beam line, all along the beam line, and enters the detector mostly asynchronously with respect to the bunch crossing. All these features will be used to try to mitigate the effect of this background. So to assess the effect, the impact of the beam-induced background to the detector response, we place a detector here in this black box and run a detailed giant simulation. The detector we are using in our first studies is basically Click's detector. It features all silicon tracking, sampling electromagnetic and hadronic calorimeters with very high granularity and fine longitudinal segmentation. Tungsten silicon for the ECAL and steel plastic scintillator for the hadronic calorimeter. The iron return yoke of the magnet is instrumented with muon detectors. The tracker, being the subdetector closer to the beam, is the one affected the most by the BIB, and the effect is the production of a huge number of spurious hits. which make the track finding and reconstruction very, very challenging. In the future, if we have a muon collider and a detector operating, also the operation of such a detector in this environment will be very, very, very challenging. Main mitigation measurements under study are a clever detector design. This is another solution we borrowed from MAP. It's a Vertex detector with a very short barrel section to avoid two very hot spots from the background in proximity of the nozzle's tips. Timing, high granularity and timing will be very important. We see that this is the heat density for each detector layer, and timing requests will reduce the number of hits by factor of 2 or 3. Very important will be the pointing, either realized either by correlating information on two very close layers, or maybe in the future having monolithic sensors capable of measuring the angle, the crossing angle. And another angle we are exploiting is the different response of our silicon sensors to signal and background particles. For example, the shape and the size of the pixel clusterings. And as was pointed out this morning, also state-of-the-art reconstruction algorithms will play a crucial role. For each event, we reconstruct more than 10,000 fake tracks, combining random background hits. But these fake tracks are characterized by very distinguishable features like very low PT or a significantly lower number of hits associated to the track. Despite the crude mitigation algorithms we are using, the track reconstruction performance is already satisfactory. These are single muons shot from the nominal interaction region. Some work has to be done in the forward and backward regions of the detector, where the heat density is an order of magnitude higher. As for the calorimeters, the energy deposited by the bib is almost uniform, both in the ECAL and the HCAL. The bib particles have on average very low energy, so they are absorbed in the first layers of the ECAL. This is the heat density as a function of the calorimeter depth. And again, will be of paramount importance also for the calorimeters to mitigate this kind of background, to have timing information, which means to request that the heat time be compatible with particles flying from the collision point. And the longitudinal shape also of the showers will be important. Just a few examples of the performance we are currently obtaining with our detailed simulation. Basically, for IPT physical objects, the performance already at this level is very good. For example, electrons, jets in the central region, while some work has to be done in the forward and backward regions. We are starting investigating the identification of heavy flavors jets. Currently, we have an efficiency of bit tagging around 60%. Here, the main inefficiency, we are using a very simple tagging technique, reconstructing secondary vertices inside the jet. And the main inefficiency here is coming from our inefficiency in reconstructing displaced tracks. And the last plot is showing the current separation we are getting for the die-jet mass produced from a couple of big quarks produced in the decay of Z or Higgs boson. The muon system, muon detectors are in the outermost part of the detector, and here the effects of background are less severe. The bigger effects are in the end-cap regions close to the beamline, of course. Here the neutrons and photons fluxes as a function of the energy for different angular regions of the detectors are shown. The bottom lines represent the central region, where the flux is low and acceptable, while it becomes worse and worse as we move to the close to the beam pipe. The performance we are getting are satisfactory. Needless to say that a muon collider detector must be radiation hard. We are studying the levels of radiation to which a detector at the muon collider will be subjected. And this is the estimate in the case of a 1.eV machine. We expect levels of 1 MeV neutron equivalent fluence between 10 to the 14th and 10 to the 15th in the tracker central region, and of the order of 10 to the 14th in the ECAL region, and a total ionizing dose of 10 to the 4th grays in the central region and 10 to the 3rd in the ECAL position. If I remember correctly, this is a factor of 10 lower than what is expected for high luminosity LHC. The preliminary results we are obtaining with the full simulation are fostering a number of dedicated and targeted hardware R&Ds. Some of them will be presented at this conference. A proposal for an hadron collider based on micro-pattern gas detectors, a proposal of an electromagnetic calorimeter based on a 3D matrix of lead fluoride crystals, and different technologies to meet the muon collider requests for muon reconstruction. To conclude, in order to fully exploit the big physics potential that a muon collider can offer, the name of the game will be to beat the beam-induced background. Our preliminary studies with the full detector simulation show that this is possible, and in particular for high PT physical objects, we are already obtaining very satisfactory results. Of course, it's easy to make assumption in simulation. Hardware R&Ds have to follow and proceed in parallel. This is happening. Most of the R&Ds we are interested in are conducted in synergy with high luminosity LHC and other future collider efforts. Before closing, I just leave as a reference information about 5 white papers we recently submitted to SNOMAS, and may offer more detailed information on everything I tried to summarize in these 15 minutes. Thanks.
Thanks. We have immediately one question. Thanks.
Thank you for the talk. On slide 13, you mentioned about the radiation dose, and you said, maybe I misheard, that it was lower than HLLHC, but I think that's not the case. I mean, I think for the Atlas HLHC calorimeters, we expect around 100 grays for the entire HLHC, and I think you have 1,000 grays per year, so it sounds like...
I had in mind the upgraded tracker detector of CMS, where I think on the first layer we are estimating 10 mega grays, something like that.
Okay, but I mean, I'm calorimeter person, so I was thinking about the calorimeters. Your calorimeters would be exposed to much more than Atlas calorimeters in HLAC, I think. That's my comment.
Yeah. There is another question.
Thanks for the talk. It's very interesting. I have a question on your slide 8. You mentioned about high granularity and also timing, so to help to suppress the beam-induced background.
Yes.
So can you please namely in quantity that how high the granularity and also the timing precision that you will need to help to remedy this background? Thanks.
We are assuming we have pixels 25 by 25 microns in our Vertex Detector, and micro megapixels in the inner tracker, 50 microns times, I think, 1 millimeter, and strips in the outer tracker, 50 microns times 1 centimeter. As for the time, most important is the time resolution. We are assuming 30 picoseconds in the Vertex Detector and 60 picoseconds in the outer tracker. And we cut in a window around the hit time, and after having subtracted the time of flight, and request it to be compatible with particles coming from the nominal interaction point. And this reduces the background by factor 2 or 3. Most affected are the first layers of the Vertex Detector. There the effect is bigger. As you move far away from the beam line, the effect is less severe.
Okay. So I think Dave is the guest first.
Hi. Can you just remind me how these background numbers scale when you go to the 10 TeV design?
Very interesting question. We are almost ready to answer it quantitatively. My naively expectation was that the higher the energy, the lower muon decays in the lab. So I was expecting it to go down. It's not the case. First, our first studies with full simulation. Now we have a 1.5 machine and a 3 TeV machine borrowed from the MAP colleagues. A group of CERN is working on a 10 TeV machine. And the answer to your question is that the background levels stay almost the same. There is a light degradation, but almost the same. And we think that two effects are compensating. As you go up in energy, you have less decays, but these few decays are carrying much more energy. And so somehow these two things compensate.
Thanks.
What happens to the neutrinos?
Are
they a concern?
Yes, they are. The point is that it's incredible, but neutrino radiation induced by neutrinos is one of the most delicate issues at the Muon Collider. Neutrinos are produced in very narrow beams, which travel inside the Earth's surface for kilometers and then come to the surface, and they activate materials. Yes, they are an issue, especially for 10 TeV or upper machines. We think that with the 3 TeV, we are already safe. With safe, I mean we are not giving to the public and to the environment a radiation dose which is higher than the legal limit of 0.1 millisievert, I think. While some mitigation measures are under study, I can say in place, are under study for the higher energy machines. One could be to move the magnets with a frequency of some months in order to spread the beam, avoid the straight sections. It's not easy of the detector, especially at the collision point. You have to have a straight. Last resort, since these neutrino beams are very collimated, the opening angle is 1 over the energy. One can think of buying the land where the it's fun, okay, sci-fi, but it's a problem we know, and it's under consideration.
Okay. there is another question.
I had the same question, so it's fully answered.
So, no, I have another question very quick again. Besides the detector, there will be also problem coming from the electrons from the muon decay to the magnets of the ring.
Yes, yes.
I read once, if I remember, that they are shot by 300 kilowatt coming from the electrons.
For a 1-point EV machine, the expected power lost into the machine elements is 0.5, 400 watts per meter.
Yeah, this is
1.5. All magnets have a tungsten shielding inside, so they have to be built with a bore larger than usual in order to accommodate some shielding. Every aspect of the muon collider complex presents unprecedented challenges.
Okay, thanks a lot again.
Thanks.
Last but not least, the Inaugural, which may make the summary of the posters which are visible in the other room. And I profit before the end to remind you that we reconvene at 3:30 this afternoon after lunch. Okay?
Okay. You hear me? Thank you. I have an unusual experience of convening myself, which is not the norm. Okay, so I have the task of summarizing 20 posters which I've not read, about 1/3 of which I understand the physics, so it's impossible. Equally impossible is I'm standing between the Italian community and lunch, so that is going to be difficult. Okay, so let's just have a look at the excellent posters which were contributed for this session, not all of which, of course, we could accept. So as you would expect, it's dominated essentially by LHC. We will see in a second, but that's not just the phase 2 upgrades, but also the current work which is going on there. But it goes a lot wider. So there are posters also talking about the other novel uses of the LHC collision regions that are not the GPDs or LHCb. We have a series of posters on not so much nuclear physics experiments as the use of nuclear physics facilities to measure fundamental physics, which is interesting. And then we have some things on the left field, which we'll come to at the end. So going through at a very rapid pace. So here we have a poster rather, the CMS Silicon Tracker. As you know, many of you were involved in this project. This is a venerable detector which has done its job and continues to work nicely to this day. But of course, like everybody who is aging, it feels a few pains and creaks. So these have to be understood very well. And some mitigation has to be taken in order to compensate for those things. So for instance, running at lower temperature. In this poster, we see a lot of detailed studies of the tracker performance. We see some predictions for run 3, and then we'll see how things will evolve. So it's a nice poster. We also have a similar poster talking about the Atlas pixel detector. Now, this is something where the radiation damage effects are starting to accumulate very rapidly as the luminosity of the machine goes up. So we gain in the physics, but we lose in the detector performance if we're not very careful. So again, this detector has to survive for the whole of run 3, and the predictions are in this poster. But you also, of course, have this detector which has to give us some lessons for what will happen in run 4 at even higher luminosities. So you see that as well. So again, a nice study. This is a poster where the conclusion is in the title, which is always advisable. The title is Atlas New Small Wheel Ready for LHC Run 3, which is an excellent statement, and one which some of us didn't think necessarily would be the case. So this is a phenomenal effort has gone into this project here, and of course we see it documented fully in the poster. So really do take a look at this one. There is the density of work per centimeter on this poster is enormous. Okay, onto the phase 2 upgrades. This is something very close to my heart. As a youth, I built the CMS Calorimeter in part. Now we have to take it out again for phase 2, and that is a large mechanical operation involving a very large piece of machinery here, and you can see some quite scary numbers on this poster. So you can see exactly how this will have to be modified, because this operation has to be carried out quickly, carefully, and without destroying anything else in the process, which will be challenging. Likewise, we have the, of course, many of you know, the Atlas ITK upgrade. Daniela's poster covers not just the design of this system and the predictions for its performance, but also some of the practicalities. For instance, the equalization of the readout rate across all of these many thousands of modules, which experience quite different conditions. So the optimization of this detector, as you know, has been a long and painstaking process, and you'll be able to read all about it in this poster. On CMS, we have the timing detector. Now, I'm sure you're familiar with the principle, but let's just state it again. So, of course, at HLLHC, we will have a very large number of overlapping collisions. So the vertex distribution will be in space, but of course, because of the nature of the collisions, the vertex distribution is also in time. So instead of simply using your spatial resolution of your detectors to cut the vertex in space, you can also use precision timing detectors to cut it in time. And then you have a 2D distribution, and of course things will become much, much cleaner. Nonetheless, this is a very challenging detector to build. It's a very challenging detector to calibrate and keep timed in. So there's a lot of work being presented here, with the target here of 35 picoseconds track resolution, which is remarkable. Now, measuring the luminosity is also important. Of course, some of the systematics in the measurements we do at the LHC GPDs are very dependent upon the luminosity. Of course, one can calibrate these luminosity detectors, such as the one you see here, but if carrying the conditions forward, effectively carrying the calibration forward between calibration events is very hard. So you can see there's a lot of work, a lot of detailed technical work going into the upgrade of the Lucid detector for Atlas. You can see replacements of the photodetectors, mechanical changes, and so this is all documented here. Likewise, we heard earlier about the Atlas muon detectors being built not outwards now to increase the coverage, but inwards to increase the performance and the coverage and take us up to higher ITER. And there's a similar project in CMS, and in fact, I walked past this the other day at CERN and wondered what it was, so now I know. So that's the advantage of poster sessions. So please read all about it on this one. And then finally, something very important. So we had a very nice talk just now about the cooling system, the front end of the cooling system with the carbon dioxide cooling, which, as we know, has many technical advantages and many advantages in terms of being able to cope with higher power densities, but also has an advantage in the sense that we are not using environmentally destructive gases in these systems anymore so much. Now, those systems also have a back end, so the engineering which goes into the back end of that system you see on this poster, and actually it's rather important. As you know, in some ways, the environmental emissions of CERN are becoming dominated by the use of these difficult materials, so this is a good development as well. So on then to the use of the LHC collisions for novel purposes. Now, many of you will be familiar with the MODAL experiment, which was originally designed to detect magnetic monopoles produced hypothetically in the proton collisions at the LHC, but which is expanded to cover a whole bunch of novel physics. So particles which leave the interaction point without direct detection will stop in a detector and then exhibit some behavior, a decay, or some other phenomenon. And now MODAL's being expanded again, so we have the detector called MAP1, which effectively increases the coverage of this for a variety of interesting novel physics. And so you can read about it in the poster. Likewise, we have PHASA, so MODAL is at the LHCb site, but PHASA sits approximately half a kilometre down the LHC ring from Atlas. So we're using all of these facilities to their max. PHASA is something which is about to start. So first splash is seen in April 2022. So does it work? You will find the answer on the poster. Go have a look. It does, which is good. So this is a very complicated detector. It's almost like a mini GPD in the sense of the tracking and the calorimeter and so on in there. Just like a GPD, when you construct it, how do you test it and make sure it works? Before you have the LHC beam, well, you go to a test beam and you do a comprehensive survey of the response of these detector elements to a wide spectrum of different particle types, a wide spectrum of energies. And of course, this is why the test beam infrastructure is so important to us in this field. So this has all been documented on the poster here, and you can have a look at the performance of the detector as anticipated, and then next year we'll compare it to the real performance. Now, this is a nice one. I have a personal interest in the poster because this is an experiment to measure the precession of the spin of baryons, charm baryons, strange baryons, produced in collision of the LHC beam with a small target. And this is actually a study I did for my PhD many, many years ago. When I did this, it required a gigantic superconducting magnet about half the size of this room. The astonishing thing to me is now the spectrometer effectively is a bent silicon crystal. And I don't know how physically large this is, but I'm going to go and look at the poster. and find out. This is amazing. So people have been talking about using bent crystals to channel high energy beams for a long time. Well, now it's actually happening. So you can do this experiment in something which is very small. And of course, it's a good use of LHCb for the downstream spectrometry. So this will be a very interesting result. Of course, one expects to see no electric dipole moment in any of these things, and you can measure the EDM using this experiment, and you can also measure the magnetic dipole moment and learn more about hadrons that way. Now, this is an interesting one, which I had to actually read the physics for in preparation. So this is an experiment on hypernuclei. Hypernuclei are nuclei where one of the nucleons, proton or neutron, has been replaced by a hyperon. So typically replaced by lambda 0. And of course, those decay. And so one has a handle, if one can track the pions from the weak decay of the nucleus, then you can do hadron spectroscopy in a brand new way. But to do that, you require an extraordinary level of precision in the spectrometry of the pions. So this is using particle physics techniques for spectrometry, all the way down in a different energy regime. And you'll see on the poster the results they obtain, which are pretty remarkable, actually. This is in the Mainz electron beam machine, which provides you a very high-intensity continuous electron beam. So it's an interesting piece of physics addressing the same goals as us, but in a different way. And here we have another experiment of a type. So again, extremely challenging. So this is now to have a look at the decays of polarized neutrons to detect the differential cross-sections of the pions, which will come from these decays. And you can see now, there's a rather complicated picture up here, which tells you can measure a whole bunch of different things about beyond the standard model physics all in one go. But in order to do so, you need an exquisitely complex detector. Now, the thing I like about this poster, and I apologize to the speaker, to the presenter, is that not everything always goes right. So if you read these posters sometimes, you get the impression that everything has been perfect and the study is finished and we continue, but some problems have been identified, and I like that statement. So let's hear what the problems are. We'll go and see the poster and ask the presenter what she's going to do about them. Okay, finally, here is a new frontier. This is the intensity frontier, but for electrons. So at JLab, we have a machine which can produce electron beams of, I was about to say astonishing, but really intensity. With those, you can explore pieces of phase space and parameter space in particle physics you could do in no other way. So the original goal was to produce intense muon beams, for which you can continue the classic studies of the proton charge radius. But of course, one produces neutrinos, around which one can build experiments, and you produce, in principle, dark matter, if some BSM models are correct. So this poster talks about the light dark matter beam, which I think is ambitious and thought-provoking. Okay, then we have LUX, which I'm sure some of you are familiar with. So LUX is going to probe the non-linear regime of QED. It's going to do that by using the electrons, which are available at DAISY, as a byproduct of the light source there, and it's going to use a laser beam in the opposite direction. So if you look at the parameters of these two beams in collision, it takes you above the Schwinger limit, and you can actually start pulling things out of the vacuum at an increasing range of masses. And of course, this is the start of a long road for these experiments. This is the first time this has been done recently. It has been done before, but recently, and with parameters. And if you think forward a few years, as the laser power increases and the beam power increases and the energy, then you can start to see that this is a brand new way of doing particle physics, which is extremely interesting. So read the poster and find out about the challenges of the detector for LUX. Then coming to the end, so some things are practical, some things have to be done. They may not be particularly sexy, but they're necessary. One of them is after you've built your fantastic detector, then you need to service it, and this is a problem familiar to many of us who are planning the LHC phase 2 upgrades, but it's a problem in Mu2E as well, where you have to get to the electronics, which has been irradiated and is rather radioactive. And the answer is use a robot. So here's the robot, and here's the design, and this gentleman here will stand by his poster and tell us how it works. Now, we had a comment earlier that we should move the design of detectors into the hands of the young people, and we should let you do the work as a training. In fact, Tommaso has a different approach. He would like AI to do the detector design, which puts all of you young people out of a job, maybe. So go and react to him by his poster. But more seriously, this is an extremely interesting thing, which has been progressing recently. So this is the mode collaboration. And of course, one is not going to design a GPD by AI anytime soon, but certain elements and certain parts of that GPD, places where you see in talks it's been optimized. What does that mean? Has it been optimized for something humans can understand, symmetry, for instance, or has it been optimized really for the physics? So this is the challenge which this collaboration is trying to answer.
And they start with a very simple model, which is a classic sort of muon tomography experiment designed to spot pieces of uranium in a light substance. And you can see this is the evolution of the goodness of fit here, or rather the metric for how good the experiment is. And you can see it evolving through many generations, and you can see the detector layout moving around as it does it. So this is a fantastic development, start of a long road again, but something we should definitely keep our eye on. So conclusions, to the extent we can form any. Just remember that all the things you see on these posters were done over the last year or 2 years. So they're all current developments being reported. That's the beauty of posters. So that means all these things were done during COVID. So it's absolutely fantastic to see that things are happening. So the GPDs are prepared for run 3, which is fantastic. They are getting ready for run 4. We see lots of other novel uses of the LHC beam, and we see lots of other things going on that currently are at a preliminary first experiment of that type stage, but which really could represent the future. So fantastic set of posters. I think all that remains, since I'm not answering questions, is to thank the poster presenters now. I have fulfilled my convenership. It is 1 minute to lunchtime.
Yes. So thanks to everybody, and I don't know if Francesco wants to add something. Remind again, 3:30 back here. Don't go to the beach after 3:30.